All right, this recording is on. So good morning, everybody, and welcome to Saturday. Welcome, Mike Fikes. We've been chatting for the last half hour or so. As we talked about, Mike is going to give an overview of the compiler today. Another thing I want to just comment on is that this is, I'm probably going to release this recording publicly, like unless somebody says something real embarrassing, then I can like edit it out or whatever. But just so you know, like I'm probably going to just share this for the whole community. I think it will be like a really good learning session. But that being said, like let's just treat this as a normal class session. This is really special. I'm just repeating myself, but it's real special, I think, to have Mike in this context because, you know, Mike has a lot of deep expertise on this topic. And, you know, we had that really, really brief overview on Thursday where like I rushed through it, you know, rapid fire. So hopefully you have some grounding of what we're going to talk about, but we can go deep on this topic and we can take basically as much time as we need. Whereas usually at like a conference talk, it's like the maximum talk you're going to give is an hour, right? So I think this topic could take more than an hour. So I'm really excited. Mike, thank you so much.
Yeah. And like, if it works, we can have like a dialogue. We could have questions about stuff because I'll try to gauge what people know. I understand a lot of the people here may be just now learning this language. So I'm gonna end up showing you code because that's the way I understand it. And I don't expect you to understand it all. And to be honest, sometimes when I look at some of the compiler code, I have to look at it again and like scrutinize it to try to refigure out how it works. It's a code base just like any other code base, right? So I can try to slow down and go and have an opportunity for people to ask questions and we can like basically in the end, hopefully you would come out understanding some of the magic that how this thing works, and maybe in a way that's useful to you, so that like as you're you know, and this is the way I feel about it as I'm doing day-to-day stuff, writing code in ClojureScript. Since I know how the compiler works, it's kind of like, I don't know, there's that argument when you're doing something, it's always good to know the next layer down, kind of thing. So that it just makes you more comfortable doing the layer that you're at, you know. So one thing I was thinking about just chatting about really quickly to start off with is just the idea that there is like this notion of a compiler, and versus like if you think about a Lisp, you could think, oh, it's very much like an interpreted thing, where the way I kind of think about it is when I was a kid, we had these basic computers and you'd flip them on and they would automatically be in BASIC, and you could type in like print hello or whatever. I don't know if you've seen that kind of pattern. It's just like you're interacting with a computer and a REPL effectively on those basic computers. And you never really thought about, well, how is this actually working? And I guess back then they were largely interpreted. And then later on, when I was in school, I was dealing with MATLAB, which is a language for a high-level language for dealing with matrices and whatnot. But it was the same kind of like interpreted thing where you're in a REPL with a prompt and you type something, you say like A=1 and hit enter, and you know it works. And I think that Clojure and ClojureScript also have the same kind of feel where you just use them. You don't have to think about like as opposed to like if you think about something like C or Fortran, there is definitely this notion that there's this compiler and a compilation step, and your code either compiles or not, and then even links the object code. So it's like this, almost like you're very much aware of that machinery, where you're dealing with the quote compiler, and you're producing something that ultimately runs, and then you loop back around and change your code. But we're all used to this idea of a REPL with Clojure, and I think that even goes back to even like the original Lisps would be very much interpreted, and so the fact that, you know, I remember when I first started getting into Clojure, Rich was you'd see him harping on or pointing out the fact that Clojure is not an interpreted language. I think he wanted to assuage any fears that people might have that it might be slow. You know, it's, you know, you want to know that like, this can compete with Java, you know, when you're thinking about, can I use this Clojure language? Is it fast enough? So he was always quick to point out that even at the REPL, when you type a form in and have it evaluate, that involves the compiler. It compiles that form. And that's true in ClojureScript as well. there's this compiler there. So and another kind of like dimension to think about this whole thing is there's this aspect of self-hosted ClojureScript. And I'll explain a little bit about that as we go through this as well. But what you end up with is you have to say, like, why do we have this compilation step? What's the deal there? And part of the answer is, well, I mean, performance and all that kind of stuff. But part of the answer is when you're trying to produce an artifact that you're going to deliver to like a web browser, you have to basically ahead of time compile it all and produce the target JavaScript language that you're going to send to that target. Self-hosted.
Can I add
yeah,
some
exactly.
vocabulary
Jump
here?
in. Yeah.
So there's like, I love what you're saying.
Mm-hmm.
There's a lot of vocabulary here, so I want to just like lay that out in case somebody is like not totally sure. So
yeah, stop me if I jump. Yeah.
So okay, so let's talk about terms like layers. Like over here, this is the CPU. This just runs ones and zeros. Okay. And then on top of that is, what is it called? Like machine code, I guess, right?
Okay. Yeah.
Or like machine code, right?
Like, yeah, the machine language, like the, yeah.
Yeah. And then we have like bytecode here. Like we're getting increasingly like higher level of abstraction.
More abstract. Yeah.
And then like, okay, so then like a traditional C compiler can take your C language and compile it to bytecode. Bytecode can go, machine code can go on the CPU. You guys are following this? We're like building up the layers. And then an interpreted language is text like JavaScript or Python or Ruby. There's a lot of examples, Lua, right? These are languages where you take the text of the language and you feed it into a program, and that program has already been compiled. It's like it's already runnable. And then that program like runs the instructions. So that's an interpreted language. So we keep going up.
Yeah, thank you, Chris. That's a good point. I didn't even think that people might not be aware of what an interpreted. Yes.
Yeah. So what's really unique about like Clojure and ClojureScript is that. So okay, let's just talk about JavaScript right for now. And imagine you're just writing vanilla JavaScript. You can just write that code, and you write your program in that. You think of that in your head, and then you give that to the interpreter, and it runs it. So we talked about this the other day. And there's that great talk or that concept, I think, in Simple Made Easy, the distinction between the construct and the artifact. So the construct is the thing between your ears, it's in your head, and the artifact is the thing you can give to the computer to run. So in the case of like vanilla JavaScript, the construct and the artifact, they're the same thing. The way you think about your program is the exact same thing you could give to the interpreter and it will run. So we're finally to ClojureScript. So ClojureScript, the construct, the thing you think about is Clojure or ClojureScript, right? But then that goes through a compilation phase to generate a JavaScript file, which is then sent to a JavaScript interpreter, which then goes down the chain and eventually it runs on the CPU, right? So we're many layers removed, here. But what Mike is saying, and I totally agree with what he just said, which is having this compilation step from your language level down to whatever the next level below is, right? And in the case of ClojureScript, it's an interpreted language, JavaScript. In the case of Clojure, it's Java bytecode. Is that right? I think
it goes straight to bytecode. Yeah,
to bytecode, and then the bytecode runs on the JVM, which is like right. Even though the compilation step results in a language that gets run in an interpreter, it's a super important and powerful aspect of the language. It's like, think of it as like, it's an opportunity for you to optimize stuff. Like if you're on a stage and you got like the audience out on stage and you got the play in the back, you can like slip in the back and grab the costumes real fast. It's, it's almost like a cheat step where you can say, here's my program. Here's what I care about in my head. Here's where it's actually running. But you know what? I can slip in right here and do some tweaks. I can fiddle the knobs if I need to. So that's a really powerful idea. Yeah.
So one thing that I would mention along this subject is if you're learning Clojure or writing a program in Clojure, there is one difference between Clojure and ClojureScript, which is the fact that in Clojure you have the entire compiler with you all the time. And what that means is you can have things like, we don't need to go deep into this, but you can have things like eval. Macros tend to work out a little bit more nicely in Clojure. And ClojureScript had a goal to target things like the web, right? You know, that was its big motivation. So that kind of informed the way the ClojureScript compiler was shaped in the end. And it leads more to this need or this benefit of having an actual ability to have like a compilation step where you spit out an output that is then used for something else. Whereas in Clojure, it's more willy-nilly, where you just use it. You forget about the compiler more regularly there. But what I wanted to say about this in ClojureScript is there's this other extreme with self-hosted ClojureScript where you do have the compiler with you. And you can do more of the things that you would do in Clojure. So what's kind of nice in the end is, like, you could argue in ClojureScript, you can opt into either extreme. You can have like this highly optimized thing where you're delivering something to the web where it's compressed down to almost nothing, and you give up certain things by doing that. You give up the ability to do eval and certain macro-ish kind of things in order to, like, and a lot of the stuff that would exist at runtime in Clojure disappears and evaporates in ClojureScript as you're compiling it down to go on the web. And that's all in the name of making it tiny. Whereas if you want, you can have the other extreme. Even in the web, you can have self-hosted ClojureScript running on a web browser where you have the entire compiler with you. And the trade-off that you're making there when you do that is that the deliverable to the web browser is a lot larger. And I think, I haven't tried it in a while, but I think if you depending on the speed of your internet connection, if you go to a web page that's, running the self-hosted version of ClojureScript and the compilers in there as well, it could take maybe a second or two, I want to say, to load it, which, compared to, like, that's not cool, right? If you want to, like, make a really snappy web interface that does something and it's got some code in it, you want it to download that in, like, probably milliseconds.
I think ClojureScript.io is that. And I think it's maybe like 5 or 6 megabytes, maybe.
Okay.
Something like that. But yeah, this is your wheelhouse, right? Aren't you primarily, don't you have, is it the Replete or what's the project that's your project where you do this on an iPhone?
So yeah. So I was enamored with the whole self-hosted ClojureScript thing. For me, it was a very geeky, cool thing to get into. I found it very intellectually stimulating to make all this stuff work. So I contributed a lot to making that. And I made a lot of self-hosted things. So what Chris is speaking to is if you want to mess around with ClojureScript on an iPhone, there's a REPL called Replete that you can get for it. And what's cool about that is when you're working with ClojureScript and you're at the REPL and you're doing the normal ClojureScript thing, you typically have a Java virtual machine with you. ClojureScript, the compiler, is arguably just a big Clojure program. It's probably one of the biggest ones. I don't know. It's a huge Clojure program. But the weird twist here with self-hosted ClojureScript is that Clojure program that is ClojureScript can also be compiled as ClojureScript. And it's a very mind-bending thing. We don't have to get into that. But effectively what it means is you can have a REPL on your iPhone that works, and you can actually type in a command. It's hard to do. It's really annoying. But you can type in a command, a form on your iPhone, and it'll evaluate it right there on the iPhone. And there's no JVM there. It's just JavaScript core running some JavaScript, really. So for me, this whole philosophical thing of, like, a compiler or not, it's kind of an interesting thing in ClojureScript where you, like I kind of said, you can opt into either end of the spectrum. You can compile down to target a web browser, or if your target is different, like if, for example, in the iPhone app I mentioned, and by the way, Replete's available for Android and also Mac OS, but it's in that target, you don't care so much. You're not trying to, like, compress down the deliverable to this tiny little thing that can be downloaded in an instant, right? When you download an iPhone app, you're willing to wait 30 seconds and then you have it, right? So I think that's kind of an interesting philosophical thing that I kind of struggled with for a while, was, like, just trying to get this straight in my head. Like, what does it really mean to have a compiler? And when self-hosted came along, it's kind of like, it kind of, like, warped that whole idea a little bit. And it's like, yeah, you can have both if you want.
Can I say 2 things?
Yeah, certainly. Yeah.
Okay. Number one, I want to emphasize that, like, if you don't really understand what we're talking about right now, this is completely okay.
Yeah.
And
I don't even understand some of it. So yeah.
Yeah. And
sure.
I've been using ClojureScript, like, for work for like 7 or 8 years now. And not until, like, a month ago that I really understood what it meant for ClojureScript to be to be able to compile itself. I really did not understand that until like a month ago. So you don't need to like really understand this to
don't get caught up on that.
Yeah. And then the second thing I was going to say was the reason I understood it was I watched this really cool 30-minute talk by Maria Geller, which I'll put in the chat channel for us, where she basically just does this on stage and explains it. And it's like, oh, that's what that means. Like, I get it now. And so I'll put, if this does tickle your curiosity, you know, bone, give that talk a watch. And she does a great job explaining it. But
yeah, I'm hesitant to talk too much about self-hosted because it's so abstract that you might just say, what is Mike talking about? And just say, whatever. So I just wanted to mention that just because we're talking about the compiler now, and I just kind of have a philosophical, interesting view on what it really means. And I think in the end, arguably, you don't want to think about the compiler. You just want to use this thing and you want it to work. But that's what we'll talk about today. Is we'll go into what it is, and so that you do have, like I mentioned, you have that next layer down view on how the magic, how the gears turn and make this thing work. And then for me, the reason I got involved in this stuff was, I guess it's going on about half a decade ago now. Back then, ClojureScript was actually pretty solid at the time, but you would invariably run into things that would break. And it reminds me of maybe those stories, if you remember hearing about like early automobiles, and someone would try to drive from one side of America to the other. And if you were to do that, you had to bring a toolbox with you because you were going to end up fixing your car, halfway across America to make it, right? And that ClojureScript wasn't that bad back then, but you had to be kind of willing and ready to like roll up your sleeves if you hit a corner case that wasn't working right. And that was why I got involved. And you'll see that when I explain this, my view of the ClojureScript compiler is really from the vantage point of someone who dives into it every now and then to try to fix things, to fix something that was bothering me that I wanted to work correctly, or perhaps to improve things a little bit. But I have not really been involved in largely structurally changing things. So my experience is largely like, just a quick dive in to say like, oh, here's how this thing works and here's how it's broken. And what you'll see is what's kind of cool about this is if you learn the Clojure or ClojureScript language, it's kind of nice that you can actually read the compiler. If you're thinking about Clojure, on the other hand, if you hit a bug in that, then you have to know Java. You have to dig down in there. And so it's kind of cool in ClojureScript. The whole thing is you stay in the same language. Another story I wanted to mention was I remember when I was perhaps like, I want to say maybe around 14 or so, and our lawnmower was not working properly. My dad was a mechanic, and I think my dad's really cheap. Instead of just going and buying a new lawnmower, what he did was he took the whole thing apart. He like got one of these like a tarp, and he laid it out on the ground, and he like took the entire engine apart and cleaned all the little pieces. But I remember this was even before computers were like, when I mentioned there's like basic computers that you could get and turn it on and you'd be in basic. This was around that time frame when those didn't even exist yet. So back then, like combustion engines were like a cool geeky technology to get into. And I think my dad was kind of into that kind of stuff. So he explained to me how this combustion engine and a lawnmower worked. The typical 4-stroke thing where you have like the intake stroke and then the compression stroke and then the spark plug fires and then, and then in the exhaust stroke, right? And I remember my dad explaining to me, like since he had the entire lawnmower apart and lying out there on the ground, he could show me like, hey, Mike, here's the part where like, I don't know the right terms for it, but like the camshaft that would like move those little valves and like let the fuel in or let it exhaust out, and the thing that would trigger the spark plug. And for me, I didn't understand that lawnmower completely back then, but it was enough where he could explain to me like, here's the rough idea. There's 4 strokes and they work in this way. And at that age of like 14 or so, I got it, I could understand it. And then he put that entire lawnmower back together and it worked, he actually like had to pull the thing a few times, but it actually like, he got it all back together again. So I think what we can go through here is like kind of an analogy where I can show you the inside of the lawnmower and explain some of it. And we can actually like, and the thing still works though. Like I'll run some examples here and there. And you can ask questions if things aren't clear, and we can kind of see how the inside of this machine works a little bit. And maybe that will help you, just be better at understanding what's really going on. And maybe you just might find it interesting. It's like an intriguing thing to like say like, that's how it works. It's in the end, like anything else in life, once you see it, it's not that complicated really. I think in particular, the ClojureScript compiler is not like, when you think about, oh man, a compiler, that's got to be horrifically complicated. And I think that's probably true for things like a C++ compiler or something like that. That's fundamentally like compiling things from a very high level language down to machine code. Whereas the cool thing in the ClojureScript compiler, it's basically transpiling from ClojureScript to JavaScript. And JavaScript has enough of a lot of the same ideas and constructs available to where the ClojureScript compiler doesn't end up being that complex. It's got it's compiling to things that are roughly at the same level. So you'll see it's not like oh man, it's not generating bytecode or something weird like that, where it's like really hard to grok what it's doing.
Yeah, I find the output from the compiler is pretty readable.
Yeah.
Let's open that lawnmower.
Yeah. Okay, so what I want to do is I'm going to open the lawnmower. I'm going to do something that might be scary to do in like a conference or whatever. I'm just going to show you the code for the compiler, and like I think we can walk through it, and you don't need to be afraid of it, right? We just go into it. So to do this, I'm going to share I guess I could share my entire screen. Or just the app. Let me see if I can figure out how to do Zoom again. Just give me a second. And I have the font a little bit bigger because I know some people might be maybe on laptops even, right? With smaller screens.
We'll give you feedback if we can.
Yeah.
Daniel, I'm jealous of your background.
That's cool.
Yeah, mine is pretty great. I'd recommend being here if you can.
Oh, that's a real background. That's not a filter. Oh,
yeah.
Man. Awesome. Let's see. I'm sorry. Let me clean up my desktop. Give me a second, because I have a bunch of files sitting there that I don't want everyone to see. I'm going to just grab them all and throw them into a folder. Yeah, cool. Now I'm just going to share my entire desktop. And then we can figure out the font size stuff. Let's see, share my screen. Okay, so now I think I'm sharing my whole screen.
We can see it.
Okay, now I can drag this to be larger, and I can make the font larger too, to kind of.
Maybe a couple notches up on the font size.
Let's try 16. Did it do it? There we go. You have to switch from buffer to buffer. So this is pretty big now. I don't know if this is coming across suitably through Zoom. I can even make it larger if just anyone yell out if it's like too small, or because we don't need to see too much to be able to look at stuff.
We could do maybe one notch up, but does anyone have any thoughts? Does anyone have anybody else have thoughts?
It's good here for me.
Yeah, I can read it fine. I'm trying to think about like the recording.
Yeah. And this is the thing, typically, like if you're giving a conference talk, you have to use gigantic fonts, right? For people to see from the back of the room. Mm-hmm. But since we're all on computers, we might be able to pull this off and see some of this stuff.
Yeah, you could also make it like, I'm not sure what you're going to do next, but you could maybe make it full screen. So we don't need to see your, whatever your toolbar is at the bottom, but yeah. Yep,
that's true too. Yeah. Okay. I don't need to update IntelliJ right now. Yeah. Okay. So, so just like a lawnmower has 4 strokes, the compiler kind of has 4 things. And maybe Chris talked about this a little bit, but there is largely, the compiler has a lot of stuff in it, but if you get down to it, there are 4 large things in my mind. And they kind of form a pipeline. Let me show you a picture.
I did, just so you know, I did not like talk about this.
Okay.
What I showed was basically we went from no files to adding some ClojureScript files to compiling it to looking at the output and then running it. So very, very high level. Yeah.
I'll just show you a web page that Michael Fikes wrote way back when, and he has some good pictures in here. And this is the one that I want to show, just kind of like as a mental or a visual of a pipeline. And effectively, the way it works is there's like one that, you know, your program goes in the front here, and then it goes through a few stages and comes out the other end as JavaScript. And what I'm going to show you is some of the main implementations of each of these stages. And we can delve into it enough to where you can get, you know, a decent understanding to know what those stages are doing and how they actually work. Then I think if you keep this big picture in mind, you won't get lost, you know, from the weeds that we'll dive into pretty soon. So let me go back to the thing. So I have basically, this is the actual compiler tree opened up here on the left. I know it's a little bit smaller font there, but the main ones are these 4 things. The first one is the reader, and then the next one is called the analyzer. And then after that is called the compiler, which is kind of a weird thing. Like inside the compiler, you have a compiler. In Michael Fikes's diagram, he called that, I think, emission or the emitter, which I think is a better name for that part. And then there's this last part here, which is the closure optimizations that get applied. So it's really, you know, this entire compiler can be thought of as broken up into those 4 files. If you wanted to ever dig into it, that's, you know, there's all the side things that exist, but you can ignore a lot of that for what we're dealing with. So if we talk about what each phase does, at a high level, the reader's job is to take the source text of your program, which is just basically like a string, if you will, and it basically converts that source text into data structures that we call forms. And I'll give an example of that. Let me bring up a REPL. Okay, so here I was already doing this prior to this. So there's a library called Eden. I'm going to require Clojure Eden as Eden, and it's basically Eden is a library that's used to read strings into Clojure data structures, and you can use this in both Clojure programs and ClojureScript programs as a way to serialize your data in and out. So for example, let's say we had some data that looked like a map, maybe. I don't know if you've covered maps yet, but we'll just put one here. A map that has a couple of keys and a couple of values. And let's say I wanted to turn that into a string. I could PR that. Sorry, PR stir. PR just shows you the actual thing. PR stir should put it into a string. So basically, this notion that this is actually now just text, it's a string, and you can use Eden to read this string back in. So if I say, and I'm copying and pasting this thing in a REPL, you can use this thing called *1 to get at the last form that you have. But the idea there is that I've taken this string and converted it back into data. So there's a fundamental difference here. This thing here, I don't know if Chris has mentioned this stuff to you yet. This is a persistent data structure. It's actually kind of like an object in memory now, as opposed to just the raw string format of the stuff.
Let me comment that this is this is very much like a JSON serialization. Like if you have some string and you say JSON.parse or JSON.stringify, and you're sort of traversing between the JavaScript object and the JSON or the string itself. If that's an analogy that makes sense for folks.
So there's a Man, if I can explain this without getting down into the weeds, but what Chris was just saying, this is actually a JSON object, but represented in ClojureScript. So that's another notion, another idea there. But let's see, what was it? JS. I want to call .stringify, right?
Oh, Daniel, sorry, I just saw Daniel has asked a question in the,
Oh, sorry, okay.
Zoom chat. By the way, Daniel, you can just unmute yourself if you want to.
Mhm.
Oh, okay. I didn't want to
yeah.
like interrupt. So you
No.
you said earlier that like basically there's these 4 steps or 4 files that are very important, and there's a bunch of all this other stuff. Could
Yeah.
you give an example of like something that's in the other stuff that's like nice or useful, but not like a part of the core, the meat of what's going on?
Certainly. Yeah. So let's see, if we go in here, CLI is a file that's used for like if you're using depth-based thing and you're like starting up and you want to interact with the entire tool chain from the command line. There's some like, all the CLI isms are in this file here, parsing your arguments that you pass in. That's not really the compiler, but it's part of the, it's part of what gets shipped. Let's see. env is a place, it's just a small little namespace that has like, we'll talk about what goes in there, but it's like a place that holds compiler state. Some stuff for parsing and dealing with externs, which has to do with Google compilation. Here's a namespace that deals with parsing instances. So like little ancillary side things that, you wouldn't really like some of these things, you would feel uncomfortable if you shoved some of this stuff into some of these other namespaces. They kind of like warrant being off on the side. Oh, here's code to run the REPL. That's a pretty big, important one, So it's just kind of like, they're not part of the compiler proper, but they kind of help make for a full-fledged thing when you get the ClojureScript compiler. Another big thing that's in there is the actual implementation of the standard library. So all the functions you use, let's see, I'm sorry, I'm in the wrong spot here. All the stuff that like map and reduce and all that kind of stuff, they're the standard library that ships with the compiler so that you can actually use this thing to write programs. That's all in the delivery, and that's not really part of the core compiler, but it's huge, it's big. Oh, speaking of the sizes of things, in Fogus's article, I noticed near the very end, he mentioned the size of the emission phase. And I think he said it was around 700 lines or so, down near the bottom here, whatever. But when I look at this picture, when I look at this diagram, sorry, I'm scrolling pretty quickly. When I look at this diagram here and I see these blocks that Michael Fogus laid out illustrating the pipeline, to me, the sizes look wrong. And I don't know if that's because things have evolved over time, but really the analysis part is huge. It's the biggest part of the whole compiler. And then reading is tiny compared to that. So I'm colorblind, but I think it's this blue part here, analysis. I would draw that box much bigger. Reading is smaller. And to be honest, it's when I have, like I said, that the reason I got into this stuff was I would go in and I would fix things or improve things. Whenever I do that, I spend most of my time in the analyzer. And maybe after we go through the analyzer, you'll start to see why. It's a pretty beefy thing in terms of like how this whole thing works. It's got a lot of the logic in it. But unwinding back, we were talking about the reader, and Chris he was kind of given an example that by analogy, if you know.
Can I add a quick thing?
Yeah.
So the kind of to answer your question, Daniel, if there's these 4 steps of the compiler, you can think of these are the 4 things that it does, 1, 2, 3, 4 in a row, but each of those steps may have auxiliary helper functions, or like what Mike was sort of showing were these namespaces that contribute to those steps and they help those steps, but they're not they're still just the 4 primary steps. There might be 25 namespaces, but there's, you can think of it as like step 1, step 2, step 3, step 4. Yeah,
like if you were to clone the compiler repository and crack it open and go look at it, you'll see lots of files in there. And I'm just telling you, you can ignore most of it for what we're talking about. There's really just these 4 files. And one of them isn't even part of the ClojureScript compiler, the reader. And I'll talk about that in a second. It's not actually part of what you get if you were to clone that repository. So I was trying to do this and see if I could pull that up. Ah, yeah, it worked. Okay. So what Chris had mentioned is in JSON, you can stringify some stuff. And this looks weird, right? It's got the quotes escaped and whatnot. But if you were to print that, it would look like a normal JSON representation of an object. You can, I can't remember the name. Is it parse maybe to go the other way? But that's effectively this notion that you're taking an object and going to a string form and back. The whole idea of reading is very much the same analogy. We're talking about reading data in, and what's weird and interesting and meta-circular about Clojure and ClojureScript is that our programs are written in that same data. So if it's kind of a geeky thing. If you look at it, if you look at like a Clojure program, it really is just a bunch of lists, one after the other, or data structures. It is all just data. And that's important to say, because that's what the reader is doing, is it's reading Clojure data, which happens to be a Clojure program or ClojureScript program.
We have only dipped our toes into that idea.
Okay.
But yeah, it's like we're swimming in that idea.
Yeah.
But we don't really know we're in water
Okay.
yet.
Yeah. And this you can touch upon macros being part of this too, and just the whole swimming around in data as being code and whatnot. And we don't need to go into that deep end yet. But this is basically the reader is the first part of the chain or the pipeline. And if we go back to the IDE, the reader is actually in another library that's been broken out called Tools Reader. It's maintained by, am I in the wrong file? Let's see. Yeah, it's maintained by Nicola Mametto. He goes by Bronza. That's his like screen name. And to me, like coming from my perspective, I'm going in to fix things. This library is practically perfect. It never breaks. I think I've seen like 2 or 3 bugs over the half decade I've been working with this stuff. And it just, and it's actually pretty small. Let's see. So I said that I thought Focus got the sizes wrong, and maybe they were right back then. Yeah, the reader is about 1,000 lines. I wrote these down. The analyzer is about 5,000 lines. So the analyzer is about 5 times as big as the reader. And then the compiler is only about 2,000 lines. And then Google Clojure, that's probably huge. That's another thing that's outside of us. It's outside of the Clojure compiler. It's written by Google. But if we look at the reader, let's see, to try to understand this thing, like we want to dig a little bit into it and see how it works. So
ask a question about what the reader does. I think you just said this, but I just want to clarify. Like, so I write my program and I'm in a text file and I'm typing. Okay. And I'm typing parens and I'm typing symbols and whatever. And I think that my program, like I'm saying it's ready. No bugs, and I'm ready to like do this. I send this file to the compiler and I'm sending a string into the reader. Is that correct to say that?
Yeah, that sounds good to me. Yeah. Yeah.
Okay.
Yeah.
Okay. That's a basic question. I just wanted to sort of clarify. It's like, when you're typing the file, that becomes a string and it gets sent into a program. And the first step of that is the
Let's
reader.
try this. Let's make a string. This is, you see what it is, but I'm just telling you it's a string. At this point, it's still a string. It has not come to life as a program yet, right? So it's just a string with some characters in it at this point. As a human, you recognize some stuff in there. But if we were to use Eden to read this,
could you bump up the file size, please? Thank you.
There. Yeah, this one can be huge. It doesn't need to be small. Okay, we can minimize that. I'm going to use *1 to refer to the last thing in the REPL. That's a little REPL trick that you can use. *2 will give you the second to last, and *3 will go even further, and that's it. You don't have a *4. That's the magic of the reader right there. What I just did was I read a string, and what I got back is a data structure. So that's like a really fundamental notion there. It looks the same really on the screen. I guess this thing here, syntax highlighted some of it, but it's really, if you say, what is that thing? It's actually a list of things. It's a data structure that contains things inside of it. So if I say, what's the first, just to kind of drive the point home, if you say, what's the first thing in that thing that we just read in, what would you think it would be? Anyone have any guesses?
Yeah, I know the answer, but somebody else has to say.
I'll be embarrassed if I get it wrong. I know. But this just kind of helps you like grok what this.
Let, sorry, not a keyword. That's a special term.
I'm with you though. Yep, you're very close. It's actually a symbol. Let. Yep. Yeah, keyword is.
Amanda, you get a gold star.
Keyword is probably a good term for that. Like in languages, like if you think about like C and JavaScript, I think they have keywords that are like key to the language, as opposed to this kind of keyword in our language in Clojure and ClojureScript. But yes, this is let is the first thing in this list. It is actually a symbol, beside the point, but it's just, that's what we call it there. It's a symbol. You can make a symbol if you quote things like that. That's the same thing there. But that is the main, it's the fundamental notion of what the reader does is it takes your program text as a string and turns it into data structures that can then be passed to the next point of the pipeline. So let's look at the, I want to look at the actual reader implementation a little bit. Like, let's say we thought that there was a bug in there, and we wanted to at least open up the lawnmower a little bit and look at that part of the machine. So this, am I in the right file? Yeah. So for me, I haven't been in here a lot. This is, for me as a compiler maintainer, this is a code base just like anything else. And because this code base works all the time, I don't find reason to ever go into it. But I do remember seeing some things in there, and it's actually, let's see, I wanted to look for, I think one interesting thing is if you're reading a number. Let's see, here it is, read number. Let's say we found like a bug and it was reading numbers incorrectly. And by reading a number, what I mean by that, if I go back to, trying to go back to my REPL here. Just something so simple as that. We're reading a form that happens to be a number. We have to deal with things like, well, what if, there's decimal points in it, of course, or signs and stuff like that. So if we go back and look at the reader, here's the read number function. And there is right here, this to me is where the magic is. Like a lot of this other stuff here is like, kind of like machinery for like dealing with the fact that it's dealing with a reader object that has like a stream of the data coming in character at a time. But if you're just looking at the high level, like what is it really doing? There's this one bit here called match number. Okay. And then it looks like the way Nicola is doing this is he's using regular expressions maybe to do this, And here's, yeah, I remember looking at this code here. It's like, it could look kind of complicated, but it's just dealing with all the cases you have to do to parse a number, really. And so I'm not expecting you to understand this code. It's been a while since I've looked at it, but it's basically, that's an example of the kind of stuff that happens. And you can even see he's got regular expressions here that helps him just, oh, I guess I just said regular expression, and that may not be a familiar topic to people.
I think it might be in this.
Okay.
This is, yeah.
Okay, so an example of this kind of stuff is like, well, what if you got it wrong? Come on, mouse. I'm trying to bring up my.
Actually, hold on. I should not have made that assumption.
Okay.
Does anybody not know what a regular expression is? Okay. Okay.
Okay.
Yeah, I think we're good.
Yeah. So, and I think you could implement a reader. That just happened. Let's just take kind of an interesting consequence that we just saw is that the implementation choice there to parse things happened to use regular expressions, which you could have, imagine you could write a reader, you could implement it in any way you want. And you could like pick apart the numbers and the digits and whatnot. There's multiple ways you could have done it. But what's interesting for us is if you get it wrong, like if your code is, if the thing you're trying to read is not well formed, if you will. So like if you try to put in something like this, I think this might trigger it. Yeah. So that is an example where the reader was fed a string that it thought was a number, or at least it started to think it was a number, and then the train went off the tracks, you know. And so you might see this in your code. If you were to type this in a REPL, it should do the same thing. Yeah. And that kind of illustrates that the very first thing that occurs when you're typing something into a REPL is that this right here is actually a string that's read by the REPL. You know, if you've probably heard the term REPL stands for read eval print loop. The very first part of the REPL is to read this string. And this is an example of the reader complaining. It's basically saying, I tried to read this thing that you fed to me, and it is not well formed. So I guess we're going back to the high level. That's the reader's job, is to basically take text and turn it into forms. A form, you might think a form is often just a list, like we showed, like the let form up here. But forms are also these lower level atomic kind of things like numbers and strings. Those are also forms. If you have a vector or a list and it has things inside of it, you could perhaps argue that the things inside are also forms. So it's kind of like a tree structure of forms inside of forms.
I've always thought of forms as it's like the most generic term in Clojure. It means any unit of your Clojure code. That's how I've always thought of it. Yeah, a form. It just could mean anything. Like, yeah, this
so here's a form. That's a form. That's a form. Maybe like
a whole program. A whole program is basically just a bunch of forms.
Yeah, this thing here. Yeah. Let that little program. That's a tiny program. It's not like what you think. A lot of times people in functional programming will refer to something as tiny as that as being a program, whatever. But that's a form. And if you evaluate it, it has a simpler representation. So that's,
we have this text, it goes into the reader, the output of the reader are forms, and then the next step. But before, should we take a break? You guys want to take a break and then talk about the next step? Or do we want to keep going?
There might be some leftover things that I want to mention about the reader.
Oh, the reader. Sorry,
I'm
moving.
No, that's fine. There's just some minor interesting tidbits that we could talk about, but we could decide if we want to do a break or not too.
Well, how much more time do you think it would take to do that?
These things that I want to show are just kind of interesting tidbits, so I estimate 5 minutes.
Let's do that and take a break.
Okay.
Yeah, cool.
So
also, does anybody have questions? Audience is very quiet today. Which is okay. It's okay. You don't have to have questions. I'm just trying to poke and prod.
I think I said it in chat, but right now one of the interesting things is just watching you work through this code and just how you grok like a code base you're not so familiar with. So
yeah, there is that flavor of where it's just like any other, like when you program as a programmer, you become familiar with a code base. Like when you have a brand new code base, you're lost, right? You have to. So like the meta aspect of this, of going through this partially is like, you can see, I don't know the reader code base that well. But I can still pick apart at it a little bit and find the one thing that I'm interested in. And that's this stuff that you're seeing is true with any code base that you deal with as a programmer. And just because it's in the Clojure language or ClojureScript language, all that's still the same. You become familiar with it. You see the patterns, the high level stuff. So the way I would kind of describe this talk or this lecture is we're kind of flying over the code base without like trying to actually like pick at the little details. And you know, I'm trying to just give like an overview of like the pieces and how they work. So the other few things I wanted to mention about the reader, they're kind of like, let's see, they're just things that you might be interested in knowing. And I'll just say them. They might confuse everyone. But there's other interesting things where like, if you basically have a keyword, there's a thing called a namespaced scope keyword where I just typed in 2 colons. I could have typed it that way. You could type a keyword that looks like foo, that whatever, you know, something like that. You can give it basically it's a keyword as opposed to a keyword just being like a by itself. you can put a keyword into a namespace basically. And the effect is that it has a slash in the middle of it. But what I wanted to say was that the expansion of this keyword where I just typed : A, that's done in the reader. So I'm going to require a namespace, and I'm going to basically give it a namespaced keyword. So I know this may be a notion that you may not have even seen yet, but the main thing I'm trying to point out is that this little string here that says set is an alias up here for what I just imported. And the fact that it's expanding out into the actual namespace, that functionality is being done inside the reader. And if we went back in that code that I was showing, you could probably find the place where it's doing that. It actually says, hey, can you resolve this alias? Can you give me back what the real namespace is for it? And the reader will take care of some of the stuff for you. And what's important is a lot of times it's good to kind of keep these distinctions straight in your head of like, what's doing what in this compilation chain? Like, where is this part being expanded out? And in this case, the answer is that it's being done inside the reader.
I have a question.
Mm-hmm.
Okay, are you saying, so double colon keywords get expanded at the reader stage? Is that
that's what I'm
the
saying,
way to say
yeah.
what you just said?
Yeah, so
I didn't know that.
And this is,
that's so cool.
Let's see. And so like knowing that is whatever is, you're not expected to know that. And a lot of times someone even like me might forget about this and like, oh, why is this part broken? Why is it not doing something? And like, oh, that's being done in the reader. And sometimes you'll see people talking about Clojure code and like, why is this behaving in this weird way? Why is it doing that? And then sometimes the answer is like, you need to know, where is that occurring? Is it at the reading phase when it's occurring? So if I think I got lucky. Here it is. I think this might be part of the answer to that. You take a symbol and it resolves it. So essentially the reader needs to know some of the stuff. It needs to know that set expands out into Clojure set. So that if you dig through here, you'll find the place where some of these things will expand. Like here's syntax quote. Let me show you that real quick. These are very deep or advanced topics in a sense. But if I were to type like this, that's a symbol that gets automatically namespaced, if you will. The symbol ABC has this. And all I really wanted to show you was that this little funky character, the backtick, is being done in the reader. That little bit of code there that I just had up there. Syntax quote is using resolve symbol. And it's basically doing it's actually talking to the analyzer at that point to know some of this stuff, like what's in play, what do these aliases expand to. But that's, I guess, the main thing that I want to show is without getting too caught up in these weird, arguably this thing is weird at your level of what you've learned so far. It's weird to me still too. But the thing I want to convey is that that's happening at the reader. Let's see. There's this thing you may ultimately learn about called gen sims, where you automatically get a new symbol each time. I'm putting a number at the end, but it's basically generating things. And these are used in macros for hygiene. But that little pound sign at the end is being done in the reader. The fact that it's tacking on extra things to make unique symbols is being done in the reader. There's an interesting concept, and these are all advanced things that you wouldn't know yet. But what I'm putting in front of this vector here is called metadata. This thing here this is too deep in the weeds, but basically it's got meta attached to this collection. It's metadata that's on the collection that's being read in at the reader time. So at a high level, if you understood what meta is, I want to say meta is being read in at the reader as well. That's one of the jobs of the readers, to take care of reading in metadata.
I'm loving this level of detail.
Yeah, so these are
this is like we have an electron microscope on the piece of the lawnmower. Like we took it apart and we have a screw and we're looking at it with an electron microscope. That's how deep we are right now.
Yeah, and the only reason I'm mentioning these weird things is that some of the stuff, like turning that into a number that's infinity, some of these weird things, or some of these things are actually they're all weird concepts that you may ultimately learn and hit upon, but I'm just pointing them out because these weird syntactic looking things that look funky, they're being done at reader time. They expand out into things that you could have perhaps typed yourself in some other way, but they're, you know, they're the job of the reader to deal with these kind of like weird annotations and metadata you might add to things. And that's all I really wanted to say on the reader, was like it's taking care of some of that other stuff. Oh, there's one more thing I wanted to mention, is that there is this thing called conditional reading, where you can say, oh, I want to write some code that will work in Clojure and ClojureScript and perhaps Clojure CLR, which is another dialect of all this. The reader takes care of, there's this funky thing you can type like this. And if I pop open, I'm going to pop open a Clojure REPL and make the font big here. If I take this same form here and evaluate it over in here, I get the number 2, because this is Clojure in this REPL here. This other one here is in ClojureScript. And what it's doing is it's conditionally reading, here it's conditionally reading the number 1. It's almost like a, I don't know, if you're programming in C, macros to pick something that run compile time to give you. So this is a read time conditional thing where it's like, hey, I want to be able to read something that knows which language I happen to be in at the time. And I get the number 1. And over here, and this is useful if you're trying to write portable code that will work in both languages, where maybe in ClojureScript, you need to deal with something that, you know, a lot of times you're dealing with interop with these languages. Clojure and ClojureScript are hosted languages that like will interop with the underlying platforms. And those interop things are where you have platform differences. And that's where you may want to use conditional reading. But
yeah,
all
of what you're talking about here reminds me of how I'd use like preprocessor defined directives in C.
Yes.
It's like, hey, when I give you this, really what I want you to do
is give me that
an alias, you know?
Yeah. Mm-hmm. Yes. I think preprocessors in C is the closest analogy to this idea. Yep. It's basically saying, hey, I need to write some portable code that can be a chameleon and shift here if I'm in this language and shift over there if I'm in another language. So that's kind of an advanced topic, but all I really wanted to point out was that conditional reading is done in the reader, as you might expect. If you dug through that code, you'll see there's a little part in there that says, hey, you know, what type of I can't remember the term that is used for it, but it'll say like, oh, is this CLJS target or whatever, and it'll take care of reading this properly and giving you back that thing there. All done at read time. So yeah, so that last 5 minutes or so, and maybe I've gone longer, that's just extra weird things that are being done in the reader, just to point out to you that beyond just normal, like what you would imagine reading straightforward forms, all the other weird stuff is being done in the reader too. The syntax quote, you know, all that kind of stuff, all those advanced things are also being done in the reader as well.
You know, it would be nice, or maybe this already exists. Is there like a place where it's a list of the things that are done in the reader that might be gotchas? And I mean, obviously you could like read the reader source code, but it'd be nice if like for an educational purposes, if there was just like a list and it's like, you know what, really these are the 8 things that happen at the reader that might be, you know, tweaks or gotchas. Maybe we should create that. That could be a student project or something.
And sometimes I'll see like, there'll be like someone will, like you'll see these every now and then someone will tweet out like, what do you think this evaluates to? And a lot of the answer is like, well, how does the reader behave for that? And sometimes it's really like interesting corner cases on reader stuff. And it's really mind twisting, like, oh, that's what the reader is supposed to do. And that's how it reads this thing. But at this level, you know, really the main thing that you want to understand is that it takes strings, which is your program text, and returns data structures, that is the forms, if you will, that would be passed to the analyzer. I guess that's what we could talk about after a break, if that's what we wanted to do now.
Thank you.
Yeah, I think if that's the end of the reader section, I think it's a good time for a break.
Cool.
Before we just do that, does anybody have lingering questions or?
Yeah, I've got a question.
Comments?
Just with forms and expressions, like those, how would you differentiate a form and an expression? If you do.
So when you say expression, let's see. are you thinking about like if I'm going to add some numbers, but inside here I have another sub expression that I'm typing. If I highlight that, that to me feels like an expression. This +2, 3 sitting inside there. Is
Yeah.
that what you mean by expression?
Yeah. Yeah.
Okay.
That's how I would interpret an expression, is like it's doing something. I'm getting.
So part of like my immediate feeling on this to help answer is that it's like this to me feels like a form that may have subforms, if that's such a thing.
Right.
Like I want to say they're the same in my mind. I wouldn't draw too much of a distinction. Like I want to say that forms can have forms inside of them, just like expressions can have sub-expressions.
I would. That is exactly how I would see it as well.
And it's a good question. Yeah, it's maybe what you're kind of hitting upon is that the language that you use for expressions and sub-expressions kind of lines up with forms and subforms.
I mean, I also think you could say that it's both, and that it's accurate to say that, like what Mike just typed, it's accurate to say that that is one expression that contains a sub-expression. It's also accurate to say that that's a bunch of forms, but the context in which you would use those terms probably depends on kind of like what you care about. So if we're talking about forms, we're probably like thinking about compiler, we're thinking about the analyzer or the reader. If we're talking about expressions, what we probably care about is like, well, what does that evaluate to?
Yes.
And but it's not that one is right and one is wrong. I think they're both accurate, and it just depends on how you're seeing it, or like the context in which you're thinking about it.
Yeah. I thought it was a bit strange because you'd enter the number 1 and you call that a form as well.
You would, in other languages, you might call that an expression. Yeah. So perhaps like if I did that, well, let's see. Well, if you say, tell me what a form is, if you asked a Clojure developer, I think, at least to me, mentally, for some reason, I think of something that's inside of parentheses. I think like, oh, but, you
think of forms in terms of macros, right? You say like and forms.
So this thing here that I'm starting to type here, I think of as it's a form, I think, oh, it starts with the parentheses and it has a thing after it. But in fact, like we're talking about now, that's also a form, the number 1. They just happen to be like more atomic. They're atomic forms.
Also, I believe, Paul, your background is Ruby, correct?
Yeah.
And I think in Ruby, everything is an expression.
Yeah. That's why I'm like pretty used to expression. This form is a new. So to use the different terms, interchangeably, it's like I'm used to expressions. I would call
If you've all used REPLs,
the forms look like expressions.
Maybe one definition of form is like what you type at a REPL is a form, right? But having said that, you can type multiple forms. I don't know if you knew this in a REPL, and it'll give you all of them. So it's just like everything has a caveat that I want to say, but that's not normal. What I just did, right? That's really weird. You may have never even known that you could do that. But what you normally type into a REPL is a form.
Right. Cool.
I love when we can connect. I love when we can connect the knowledge that we have with the languages we're familiar with Clojure, and say, you know what, those like, are you familiar with this concept here? Guess what? Very similar here. And then sometimes it's like, hey, this is a new concept, and by the way, it does not exist in the language that you're familiar with, right? And I like being able to make those connections, or like the lack of connection, I think is also kind of valuable. Cool. Okay. Anybody? Anything else? Or I think a break is good. We'll just take a 5-minute. Yeah. Jock says yes. Cool. I'll refill my coffee. I'm gonna pause this. I'll pause the recording. Let's just chill out, and then what happens? Stay tuned for what happens after the reader.
We're a quarter of the way through, but of course I said the analyzer is big. So we can take as much time as we like. Then
this is great. Oh yeah. I have already learned something. This is great.
Cool.
Yeah. Okay, I'm gonna pause.
Okay.
And we're back.
Okay.
And we know that you type text into a file, it goes into a string, and it gets read by the reader, and the reader converts it into data. And then what happens next?
Yeah. What's the next part of the lawnmower engine?
Yeah.
And so the analyzer is the biggest part in my mind. It is in terms of number of lines of code. It's the place that I most frequently go if I'm working on the compiler or fixing things, or just, it is the thing. And so we'll probably spend the most time talking about it, if that's cool. And I don't mind talking forever or long. We want to talk. If you're like tracking time and you're like, hey, wow, Mike spent like an hour on the reader and we're still in the middle of the analyzer, just know that the emission part is actually simple. So if we're like in the thick of the analyzer and you're starting to worry about like, whoa, how much time, it is the biggest part. And so just expect it to take more to talk about. And it's the funnest part to talk about. It's where all the cool stuff happens in the compiler. And the way I would kind of explain it, one way to look at this is the analyzer kind of like, we have these forms that come out. If we go back to our lead example, scroll all the way back, like this example here, and we read that, right? It's in the history somewhere. We read that and we got back this form. Let me get it again. The question will be, maybe I'll just type it in again. So we have our program text. This is our little program here. And we read it. And we now have something that looks much more, something that we can work with. It's a form, right, in the compiler, instead of just a string of characters, right? And we can do things like we said. We could do the first of it. We can now start to talk about the things inside of it. But this is devoid of any meaning. Like you and I know what let means, but the compiler doesn't yet know what let really means. It's a form. It's a data structure that happens to have, this thing. If I describe that, there's a symbol sitting there. Here's a vector, and inside that vector is another symbol and a number. And there's another funky thing, it's an application of a function called plus but even that, like it's not really even that yet. It's just that thing that I have highlighted is a list that has the symbol plus, followed by the symbol X and the symbol and the number 2. So the analyzer's job is to take this form and analyze it for meaning, basically. It looks at the things and it has some understanding of stuff. And what you end up with is what's called an AST, an abstract syntax tree. One thing you could look at is like we were talking about expressions and sub-expressions, forms and subforms. You could say, well, this is very tree-like, right? It's got some high level structure and some sub things in it. And that's true. It does have, you could think of it as an AST if you'd like. But the AST that we produce in the analyzer is like rich with meaning, and it's got a lot of stuff in it. Focus's picture might be a good picture. Here's a picture of AST. Oh, it's using let too. This is great. Let me zoom in on this one, because this is probably a good mental image. The AST is actually Clojure data, but Focus has it kind of diagrammed out here in this interesting way of looking at it. Really, the AST would be like a map with submaps of all types of information in it. And we'll actually we'll have the AST be produced for us so we can see this kind of thing. But it's good to just kind of look at this picture and think, oh, if we were to analyze, maybe Focus had another let form that he was analyzing here, but it's not that important. But really what you end up with is a let form has inside of it bindings, and bindings means the, if I go back to here, this is a binding. I'm binding the local symbol X to the number 1 in this form here. I'm telling you that as a human, right? And you know that what that means, but we have to actually make the machine work. So it, in AST, it encodes that into the AST as a key in this map called bindings. And it has, oh, okay, the name of the binding in this case here would have been like X is the name, and the op would have been a constant as well, and the form of that constant would have been 1, the number 1. So it's kind of like you can start to see how, even with what we've discussed so far, it's like it's taking this let and breaking apart a little bit of its meaning. It's no longer just a symbol and a vector following it. It's something in there new that that the thing after the symbol let is bindings, right? And essentially at the highest level, that's what the analyzer really does, is it basically takes your forms and expands them out into this data structure, this map called an AST that has meaning. And that meaning is important because it's used later on when generating the JavaScript code. But it's also used in the analyzer for lots of other things, like producing errors for you to see like how your code might have been wrong. Type inferences in there. We'll touch on some of this stuff. But this is where all the fun stuff happens, is like the meaning of your code. So I think maybe the next thing to do would be to, well, maybe I'll show it to you here and then we can dive back into the lawnmower engine. So let me just see, I have a cheat sheet here. I'm gonna have it analyze something for us and give us the AST.
I'm like unreasonably excited to see this.
Okay, yes. So what I'm going to use is, I'm actually going to use self-hosted ClojureScript to do this. It's not important, but what I'm going to do is I'm going to do it in a way that's easy to do right at the REPL. So we can kind of see the gears of the lawnmower turning inside. And let's see, so in my cheat sheet that I have here, I'm going to use a function called analyze string, and inside of analyze string, it'll read the string into a form and then analyze it and give us the AST back. So let's start simple. Actually, I need to give it some state. I'm going to give it an empty state. That's not important for what we're talking about here, but I'm going to give it the number 1 to analyze, and I'm going to tell it. It's gone off the edge here. Okay, context expression, and then let's see. There we go. So this is big. I know. I'm gonna get it to there. Now it's more nicely formatted so we can see. So I analyzed a form. Sorry. I am in the Plonk REPL, and I basically took this thing that it printed, and I basically pasted it back in. And Plonk,
then it pretty print.
Yeah, Plonk will automatically always pretty print things for you. Another way to do this would have been.
If I can make an analogy to this, because we have not even really seen a REPL yet so far in class, but if you're familiar with Chrome Dev Tools, I imagine there's some people in the audience who've like used Chrome Dev Tools. If you like console log an object in Chrome Dev Tools, it'll pretty print and expand it, and you know what I mean. I just wanted to draw that analogy to this.
And I like to think that I'm clever, but I can't grok this. This is just a wall of nothing to me. I can't see what this is. I love this Clojure language and that it's a data-oriented thing, but this way of seeing it is just, man, I can't visually see what's going on here.
It's almost like there's a relationship between indentation and structure, huh?
Yeah.
Par infer.
Yeah, that's right. So we analyzed just the number 1. And we got back this pretty big thing just for the number 1. But what it's trying to tell us here is that this is a constant, basically, and it's telling us what it is, what its form was, what its original form was. Oh, it's got tag nil. I expected it to know that it was a number. Interesting. This tag would have been the type. I mentioned type inference, and then some other stuff in there. But really, we could even analyze other things that are more complicated. Let's see if I have my thing. I apologize. I'm going to go back. And you'll just be horrified at how big this is going to get to be. Let's just do that. Let x equals 1, x. And it just gets to be so huge that you can't really see it. But it's basically, it's better to look at this diagram here. You know, it's basically a map. And if you're working in the analyzer, you'll start to learn these bits here of the meaning. And you can then imagine that analyzer code can do things based on the meaning that's encoded in here. But fundamentally, let's just crack open the analyzer so you can see perhaps how it starts to form this stuff. So let's see, we will flip over to, did I close it? I'll open up again if I did. Let's see, analyzer. There we go, analyzer. Okay, so this is the analyzer. It's the biggest one. It's about 5K. I'm going to go to the very bottom to give you a sense of where it all starts. Sometimes Clojure code is best to read from the bottom up because the fact that functions in Clojure refer to other functions that are higher up in the file. And this very bottom function here in the analyzer is called analyze file. And yeah, this is a pretty big function, but the key bit here, which may be of interest, is that right around here, it forms a, didn't want to move any code around. It creates a form sequence using the reader stuff. And for each form that it sees, basically the way Clojure works and ClojureScript, it's actually, you think of it, you'd like to think of it as an imperative language. I'm sorry, as a functional language. But in this sense that I'll describe, it's very imperative, where a file in ClojureScript is basically a bunch of forms, right? One after the other. Like this thing we're looking at here. This is a bunch of forms. Here's a form. I have it highlighted right there. That's a form. And that's all a file really is one form after the other, a sequence of forms, right? And the analyzer is going to loop through and analyze that sequence of forms. And what's imperative about this is that when the compiler compiles things, and this is true in Clojure too, it's basically evaluating each form in this file simply for its side effects. So one after the other, it's evaluating them. They're not really printing anything out to any output. There may not even be a REPL connected, right? When you're compiling, it's just evaluating each form one after the other for their side effects, and that's very imperative. What it's doing, it's like it's going through, and the side effects are. Does anyone have any idea what a side effect might be for this, or what a side effect really is? And like, if I were to evaluate this, what would be the side effect of evaluating that form? As opposed to, for example, if I were to evaluate, just to give you a hint, if I evaluated the form, which is the number 1, I could have that sitting in the file. This is perfectly fine in my Clojure code.
I don't know. I mean, is it going to be, at what point does it emit the JavaScript? Like that's not. Yeah,
and that's so even just backing up away from the way this compiler is implemented, if you loosely talked about how Clojure works in our minds, you know, for any given compiler implementation, as you know, this is just a general statement that's true about Clojure. As you evaluate forms in like your program text one after the other, or as you evaluate forms even in a REPL, which is kind of largely the same thing. You're just going one after the other. You're evaluating those forms. Oftentimes you're evaluating the forms to see what they evaluate to, right? You're evaluating some expression that may evaluate to some interesting value. But a lot of these things, you just evaluate them and they have a side effect by evaluating them. I'll give you a hint. If we go back to a REPL, which I'm arguing is the same thing, if we go back into this REPL here, let me kill it. So here's a very, very simple example. If I evaluate this form, it will have a side effect. It will change the world. Not in a big way, very tiny way, but it will have a side effect by simply evaluating that form. If I evaluate it, I get back a value. Yeah, it evaluates to a value, but something else happened when I did that.
Are you referencing the tree?
No. So I'm sorry. So I'll give the answer instead of beating around. So what this did when I evaluated this form was it defined a new var in my namespace. So if I do, I now see that there's a new thing sitting in this list. For example, if I do fb2 and then I do dir again, I now have two things defined. So the side effect of evaluating this form was to create a new var in my current namespace. And that var has a value. So if I evaluate it, A will evaluate to 1, B will evaluate to 2. So in particular, forms that involve def define something new. And the side effect of evaluating that form is to define a new var in your namespace. And that's fundamentally a side effect. So as any any Clojure code or ClojureScript code is being compiled, if you will, if you give it a file, here's my namespace, please evaluate this. All it's really doing is going down one to the next, evaluating those and producing side effects. And the side effects typically are defining new vars in that namespace, really. And it's really a simple model. It's kind of like going back to the idea of like compiler versus interpreted language. For Clojure and ClojureScript, you could have an interpreted form of these languages. There's nothing to stop you from having an interpreted Clojure or an interpreted ClojureScript, where as you evaluate these forms, the interpreter interprets it, and the result is that it defines a new var in the namespace.
This is really interesting. So I've never thought of it in that way. I have never considered that the evaluation of like def forms is causing the side effect of like creating vars in a namespace. And I guess I'm thinking about this right now. The reason I think that's interesting is that it's almost like the fact that you can be like productive and write code that works and not even know what like that means. I mean, like you probably need to know what a namespace is, like where like, to be, namespaces are a thing that you need to sort of understand, but I don't really like the day-to-day experience of like writing a web application does not really like mean that you need to think about vars or at least to me. So that is like totally a new concept to me.
Yeah, exactly.
Makes sense.
You like, so for example, my children are like 14 and 16 now, and even like a year or two ago when I like to explain Clojure to them every now and then. They're starting to learn, Java and whatnot. And at their age, I would never explain something like this to them. Like, it's that notion like, oh, I've just defined a function. The function now exists. And you use it as a user. You're just like, you don't second guess it or question it. But since we're talking about the compiler and how some of the machinery works and how REPLs work, I'm telling you that's what that is the mental model that you can have. Is like when you think about a source code file, and if there's a thing called require in Clojure and ClojureScript, you can require another namespace. Mentally, you could think of that as simply saying, "Hey, compiler, go get this file that has all these forms in it and evaluate them one after the other." As a matter of fact, you could manually do the same thing. You could go open that file and copy and paste in each form into the REPL one after the other, and the effect would be the same in the end. You would have the same side effects of all those forms being evaluated. And really, it's defining vars in your namespace. And that's if I tell you, hey, Clojure is fundamentally imperative at this, in this perspective, it might upset you because you've been sold to believe that we're dealing with a functional language, but the REPL and the way this works is very imperative, and the REPL becomes very stateful. You'll get into places where your REPL is completely messed up. Like you've defined a function and then redefined a different one, and you have leftover functions or leftover vars in your REPL. Very stateful, very imperative. And the functional part happens kind of at maybe the next layer down where you're evaluating things.
So just on that, Mike, if you write some code that wants to reference another function,
Yes.
you have to have already defined that function higher up in the code.
So I'm going to do that. I'm going to define a function that calls another function that would, like exactly you say, bar should have been defined higher up in the code, right? And if you don't have it defined, it will complain to you and say, hey, you're using an undeclared var, you know, it hasn't been defined yet. That is kind of exactly like what we're talking about. If I had done this in the right way, I would have defined bar first, and it would exist by the time this thing got evaluated, right? And so the ordering of these defs is such that, you know, that's like a chain of imperative stuff that you're going through. Yeah. And the ones at the bottom kind of benefit from the things that have been defined above it in the imperative sequence as it went through that.
Yep. So it won't go looking.
Yeah. And there's a thing where you can declare something. If you need to break this ordering, there's a thing that you can do in Clojure called declare. You can declare something, and then I can now use it without having defined it yet. What did I do wrong there?
There's an interesting thing about declare here. So that I created an exercise called CLJS 101 that the students got on Thursday. And what I'm asking them to do in code comments is to basically define a bunch of stuff, right? And they're just learning the language. But I have a test suite that tests that they do that. And then like the goal is for them to get the test suite to pass by just defing a bunch of stuff.
Okay, yeah.
But what I have to do is I have to declare all the symbols at the top of the namespace. Okay. Otherwise the testing namespace, which requires it, won't compile, because it's like, oh, that symbol doesn't exist in that namespace. Yeah. So at the top of all these exercises are like declare statements. Yeah.
Okay. So one thing I'd mention about this too is that we got a warning back here when I did defen foo calls bar. This warning that I have highlighted right here is produced by the analyzer. And another thing to say about ClojureScript, and I think this is true about Clojure, is they're very forgiving. This is just a warning. It's okay. It's not an error. ClojureScript has, and I had a hard time dealing with this until, oh, by the way, if you see a tail, that's my cat. He decided to join us too. I struggled with this coming from a background of languages that were very, what's the right word for it? But like they wanted to like error out immediately for you. Like if you got anything wrong, you're done, you know, compilation over. Whereas in ClojureScript and Clojure, more easygoing, you know, like the ClojureScript compiler is going to assume that you know what you're doing. It's okay. And the fact that like, if we call foo right now, what will happen here? We haven't defined bar yet, so it can't do it, right? Oh, we get undefined is not an object. That's a JavaScriptism, but it's basically trying to call something that's not defined. But what I wanted to point out is I can imperatively change the environment. I'm gonna make bar return 1, and then I'm gonna call foo right now, and it'll work because I've done it after the fact. And that's just an example where like, the compiler is cool. It's not gonna, it's just a warning. It's saying, hey, and the compiler is kind of needs to be a little bit lax at times, because sometimes you will use things that the compiler doesn't really know whether or not they truly exist, especially with interop and whatnot. You might be writing some code that will use something, and the compiler or the analyzer might say, hey, this thing's not defined, you know, and it takes a more lax attitude, and just a lot of things that you might think are just outright errors are actually just warnings. But to be honest, you want to do these things, like Amanda said, in the right order, so that, you know, the imperative things are done above, and then you basically have your file mutating the environment as it's going along. That's the mental model. Now that, you know, when you're compiling ClojureScript code to go in a web browser, you're compiling ahead of time. You know, you're going to produce a JavaScript artifact that's going to go out there and run in a browser at runtime later on. So there is some interesting thing going on here where, like, as you're compiling it, there's no runtime at all, you know, to like mutate as I'm describing the mental model as it's going through. because the runtime doesn't exist yet. It's going to be later on when someone loads your application in their browser. So there's like this interesting thing in ClojureScript, and this goes back to the compilation model where it's like ahead of time compilation. It can produce things that then later on would have a runtime. I think it's fair to say that that's not true in Clojure. I think as you're like loading Clojure code, it is mutating the environment, more like the mental model I described, where it's like very imperative and going through one by one. So that was a tangent, I guess. If we go back to the analyzer, I was down in here. If we unwind the stack a little bit and come back down here, the analyzer goes through and it gets all your forms in your code, and for each one, it calls analyze on that form to produce an AST. And that AST is that big tree of knowledge that comes out of it. And then if you look at this code, you might be a little confused. You might say, well, what does it do with the AST? You know, and effectively, if you look at this code, it's a loop that's looping around, and it's basically just analyzing stuff. In the end, it's just analyzing these forms for a different kind of side effect. It's analyzing them so that the analyzer knows about what the form is, and that it basically, the side effect is that it's basically producing parts of the AST that it then collects and it puts into this analysis environment. So it's kind of like a one level meta up. Inside the analyzer, it's analyzing things not to, you know, we're not in the like runtime environment yet. We're just analyzing things so that we can collect information about each of the forms in your file. And that information gets stored in a big atom, which you may not have learned about yet. Chris, they haven't learned about atoms yet, right?
No, they have not.
No, okay.
Honestly,
so,
we haven't even learned like let blocks yet.
Gotcha. Okay.
So yeah.
So it's basically collecting state as it's analyzing it, and it's putting it into this stateful thing called an atom to hold it. But I'll just show you what that looks like. Let's see. I'm looking at my cheat sheet again to get the right place where this atom is. So the analyzer has, I think it's in this env namespace. And this is an example where like, I deal with this compiler a lot, but I haven't memorized it completely. So I don't remember where all these things are. I think it's in, there we go. This guy here, CLJS env is it's basically this atom thing that I'm describing. And as the analyzer is analyzing the forms in your file, it's putting things into here. I'm going to look at the keys that are in the map that's being stored in here. Bunch of stuff's in there. There are, let's see, namespaces. What I'm doing here is I'm basically pulling out inside of here. Keys is a function that will tell you what the keys are in a map without seeing the whole thing. And I'm basically saying, hey, in this thing, give me the namespaces map that's under this key, and let's get the keys of it. And inside there are all the namespaces that have been analyzed that are in play and available. And so the analyzer, if we were to look inside of those, like if we were to look at, oh man, there's a lot of them. If we keep going down, inside of each of these namespaces are defs, like little maps that hold the defs of all the defins. So the analyzer is just building up this rich tree, and at the bottom of all this are like ASTs, if you will, for each of the things. So as you're like, if you define something, if I do this, you know, I define a function, the result of that is that, and because the compiler is working while I'm using the REPL as well, it analyzed this thing and it added a new thing to this big compiler environment map, if you will, just collecting up the analysis data at a high level. And the if I try to answer a question that might be in your mind, is like, why? What's it doing? Why is it building up this stuff? One part of this stuff is that the analyzer data is useful to you as a programmer and used by the compiler to give you information about other functions that exist in other namespaces. So if I for example type dir, if I require some namespace, right, and then I do dir, right? You might say, how does dir work? How does it know what functions exist in this namespace? Well, the answer is quite simple. All that dir did was it looked into this compiler atom that has all this stuff in it, and it said, okay, what are all the defs in that namespace? And let me just list them out for the user here at the REPL. And furthermore, if you were to say like doc on one of these guys, these strings and all the metadata like that tells you what the argument lists are, those are all analysis data. They're in the analyzer. You know, they're collected in this gigantic map. And there's a thing called an arity error that you can have occur to you. So if I say, if I'm going to define a function, I like to use foo. Every time I do this, I'm redefining foo to be something new, right? But if I define a function that returns a number 1, but it takes 2 arguments, right? If I call it, all's good. But if I then say, let me give it 3 arguments, that right there was called an arity error. I passed the wrong number of arguments to this function. The fact that this warning could occur is being done in the analyzer. And I'll show you that part of the lawnmower engine too. But it's basically that the fact that this foo function takes 2 arguments is metadata that's been analyzed and stored in the analyzer alongside the AST tree. This extra information is in there as well.
If I could quickly connect something, I want to connect that to the thing you said at like the very beginning. Remember we were talking about like how JavaScript is just you write your program in JavaScript and you run it in the runtime and it's kind of the same thing. Mm-hmm. And then we said that ClojureScript has this compiler step, which is like an opportunity to add like power and functionality, and it's like a beneficial positive thing. This is a really good example, and it's kind of a small example. This isn't like make or break your program, but this is an example where the JavaScript runtime does not care about the arity of the function. You can have a foo function in JavaScript, you can call it with however many arguments, and it just, it's just gonna run, it won't yell at you. But because we have this compilation step and we have this data in the analyzer, we have like an opportunity here to like help ourselves as programmers and be like, hey, you know what? You messed up. Like you said, this function had 2 arguments, you called it with 1, and you should probably fix that. So in this sense, I think you can make the case that this is like, this is better than the JavaScript runtime, essentially. But I just wanted to point out that this is like a small example of how, hey, it's really nice having a compiler at your disposal for your programs.
Yeah, it's basically doing static analysis on your program code and helping you with warnings and whatnot. The interesting thing about that is that Clojure and ClojureScript are a Lisp. They're Lisp languages, so they're very hard to statically analyze at times. They're very very malleable language. This is a very malleable language that has like I can do def, let's say G to be a function that takes an argument and returns 1. At this point, I've now defined a symbol G that just happens to have a value that's a function. What I'm trying to explain here is it's so loose that sometimes it's hard to even analyze these things and statically come up. So the analyzer will analyze stuff insofar as it's possible to analyze it. I'm trying to come up with a good example of this kind of stuff, but you can. Oh well, let's say I define a function. I'm gonna use foo again. That takes another function, call it f, right? And inside of there, I'm going to call f with 1 argument, right? Here's an example where the analyzer does not know how many arguments f takes, because it can't know. It's just been passed in as a function, right? And at this point here, it doesn't know if this is right or wrong. It's just, how would it know? It doesn't know that f, like I could pass in, something that takes 2 arguments, I'm going to pass in bar. So I'm going to take foo, and I'm going to call it with where f, the argument, is going to be bar, this function. So I'm passing a function into a function. And it's okay. I guess this is probably because of the thing that Chris mentioned with JavaScript. JavaScript doesn't care. Bar actually takes 2 arguments, but when it went to run this, it's down at the JavaScript level. It's like, it called it with 1 argument, and it came back okay. If you do this in Clojure, this is just an example to show you the difference. I have a Clojure REPL going on over here. This is an example of the difference in the runtime that Chris alluded to. So I'm going to define foo like this. And then I'm going to define bar that takes 2 arguments. And then I'm going to call this. In Clojure, that
is a cool example. Like
the arity stuff has been retained, and it's implemented in a different way down at the JVM with bytecode. So the arity error, the ability to have an arity exception, persisted all the way through to the runtime. In ClojureScript, you can get that to occur. And I'll just go into a side tangent to show that. There's a thing called multi-arity functions. So I'm going to redefine bar now to take potentially, let's say I want it to take potentially 1 argument or 2 arguments. So the way the syntax to do this is like this. If I want it to take 1 argument, I'm going to have it return 1. And if I have 2 arguments being passed to it, I'm just going to choose to return the number 2 from this function. Okay. So what this means is if I call bar with a single argument, I'll get back, it'll basically use this path here and return the number 1. If I call bar with 2 arguments, it'll go down the other path and return the number 2. This is probably valuable to show just because it's good to know. I know this is advanced.
Make a comment.
Yes, yeah.
If I were to say in Java, I believe we call that method overloading. There would be a lot more lines of code to be able to do that.
That's true, yeah.
That just is kind of stunning to see that.
Yeah, so it is true that Clojure and ClojureScript are much more succinct compared to languages like Java and method overloading and all that kind of stuff. The most extreme example in my mind is if you wanted to, in Java, create a static final class that has immutable fields in it and has a constructor and print functions and all that. You can do that with 1 line in Clojure. You can do that one single thing to find an entire class that has all this stuff in it. It has a single field named a constructor. The fields are final, so all that, and that's generally true. A lot of stuff you'll see in other languages, they're much more verbose than the stuff you can do in Clojure and ClojureScript.
Is that a macro?
Yeah, I'm sorry. I'm probably throwing a lot of advanced things that you're like, well, what did Mike just do? Def record is a macro that expands out. I'm going to macro expand that thing, just to answer your question. And it will expand to a whole bunch of stuff that did all the stuff that, if you're a Java programmer, you're like, yeah, I got to write, maybe not that much stuff, but you got to write a lot of stuff. Like in Java, you typically have to write a proper equals function, all this type. I think other languages might have this. Ruby may have some ability to define these things. I'm not sure because I'm not a Ruby programmer, but certainly Java is very verbose when it comes to this kind of stuff. And I think JavaScript is also. But going back to this multi-arity thing, remember we got an arity error in Clojure and we didn't in ClojureScript. Now that I've defined bar to be multi-arity, there is a remnant of these arities left in the runtime, and that causes it so that if I now do foo, let's see, I tried to make a call foo bar. Did I lie to you? Let's see. Oh, it takes one argument. If back here, let me redefine bar to take maybe A and B, 2 arguments. Because it accepted a single argument, it didn't do what I wanted to show you. Now bar takes 2 or 3 arguments. And if I go back and do this thing here, remember foo is a function that will apply 1 argument to its argument. Now we'll get an arity error. And that's simply, I just wanted to show you that it's not the case that you will never get arity errors in ClojureScript. The first time I showed that to you, you didn't get it because it just implemented it in Java and it trusted you. It thought that you were going to do the right thing. And in this case here, because of the fact that bar has 2 arities, one of the arities takes 2 arguments and one of them takes 3, this function now, when it tried to apply a single argument to it, it derailed internally because of the fact that, the way it all is all implemented, there has to be a dispatch to the right arity handler, and there just isn't one, So now it knows at runtime that it's not there. So backing up, what I was just showing you was some runtime facets of this. If we back out of this a little bit, the analyzer, the reason I was going down this path is the analyzer, part of what it does is it collects up arity information where it can. And I think, so for example, we have bar here defined. The analyzer should now know that it takes 2 different arities. So if I try to call bar directly with a single argument, not only do I get the runtime error that I had, but I also get a warning from the analyzer because it knows this. And that's what I was really trying to illustrate, is that as the analyzer is analyzing, not only does it produce this AST, it produces rich information about your defs, about your vars, like the arities that they take. It has the documentation strings that you may have supplied. Those are stashed in there. So that the analyzer is basically this rich trove of information that the compiler can use, which you don't, I think in JavaScript, you don't have this. Like you just go to call a function and it either works or it doesn't, right? I imagine you could devise some sort of interesting JavaScript environment that it could look at things statically and warn you about stuff. But this is not the normal case with JavaScript, right? And in ClojureScript, the analyzer basically is collecting all the meaning about the stuff that you've fed to it. So the thing that I was just showing you, if we go back into the Lawnmower engine, all the warnings, to kind of make this simpler, the warnings are near, I'm scrolling back. I guess I'm gonna have to grab the thing to go up. But the warnings, if you're ever curious, all the warnings and that kind of stuff are all done up here at the top of the analyzer, or at least they're defined here. All of this stuff right around in here inside the analyzer is all the warnings the analyzer can emit. And it does this because as it's analyzing your code, it's developing meaning about your code. And that's the point when it knows your code is wrong at times, or potentially has an error. And that's when the analyzer can, at analysis time, say, hey, I see something that statically is fishy, and it's going to spit out an analyzer, a warning typically. Sometimes it'll be an outright error where, you could type in something that the analyzer just cannot, it can't take a lax attitude. And it has to say like, I'm sorry, I can't analyze any further, and you'll get an analyzer error. But most of the time, almost all of this is warnings. If you kind of like, if you want to be really careful and you want no warnings to appear in your code, you can turn these warnings into errors if you'd like. There's some blog posts out there that show you some of the configuration you can use with like the different compiler tools you might be using, like if you're using Lanigan or Shadow CLJS or whatnot. There's ways you can instruct the compiler to like turn these analyzer warnings into errors, so that if you're like trying to like upon check-in of your code, you don't want any analyzer warnings. You can basically have it fail at that point and have an error, compilation error, effectively. So even though I described that all this stuff is very loose, there's enough in there to make it more strict if you'd like.
Can I ask a sidebar question, which is, do you know off the top of your head if does CLJ Condo use information from the analyzer to do its
Oh,
work?
that's a good question. So Chris is speaking to like a tool that's a linting tool called CLJ Condo, written by Michael Borkent. That's really nice and very powerful. And the question is, does it use, I think CLJ Condo works against Clojure as well. So maybe it's got its own, there is a thing called Tools Analyzer that it may be using. There's another library. Like Nicola, he broke out the reader that I showed you initially. Nicola Mameto also has a Tools Analyzer that can analyze code for you and produce an AST. And perhaps CLJ Condo uses that. But yeah, it's an interesting thing because like even in, for example, I'm using IntelliJ's, I'm using Cursive. The plugin that I'm using here is Cursive to write code in here. And if I do, if I define a function that takes a single argument here, and then I do,
I think I just answered my own question. I think that tools.reader, I think that it uses tools.reader.
Oh, okay.
Yeah. I'm like,
or tools.analyzer maybe, or yeah, it's an interesting question. How did he pull that off? I think
I'm not sure that is kind of it's kind
of
a,
but it's an interesting question. Like the thing that CLJ Condo does is it has to analyze your code to come up with the same kind of meaning. And what I was showing here is that when I typed this in here, this little squiggly that appeared below the foo is basically Cursive trying to tell me that I have an incorrect arity. So Cursive has its own analyzer. It's not using, it does this for Clojure code as well, you know? So this notion of analyzing your code is done by these tools as well, sometimes in their own ways. Yeah. So let's see, what else did I want to show you? There's quite a few things in here. But so at the bottom, we say, okay, it starts off, it loops through all the forms in your file and analyzes each form. And the side effect is that it collects up analysis information and it shoves it into this gigantic map. Oh, I never showed you the gigantic map. Or did I? I showed you the keys to it. I showed you the keys.
I think we maybe saw an early version of this, right?
Okay, so I showed you the keys. I just want to do this just to show you how big it is. I'm going to show you the entire thing. So I'm just dereferencing that atom to just get the entire map out of there, right? And there it goes. This is basically, I wonder how this works on Zoom, how you can, if you just see stuff flashing by. But it's basically spitting out the biggest map I've ever seen in Clojure in my life. You know, it's all the defs and all the forms and everything that this REPL knows about for all the namespaces that are in play and usable, all of it. And my fan on my computer is starting to spin up as it's doing this.
Okay, can I ask you another kind of like off the wall question? I saw when you dirred the namespaces in cljs.user that FIP was in there. Does that mean that you're using the FIP library for the pretty printing in Plonk?
Yes.
Okay. I saw that and I thought maybe that was the connection, but I wanted to clarify.
Yeah. So Chris is referring to, so Plonk is a REPL that I wrote that is self-hosted. Brandon Bloom wrote a library named FIP, which is a pretty printer library, which basically takes your normal forms and prints them in a nice way with indentation. And FIP is got this nice quality that it's rather fast and highly performant. So the thing that I just evaluated, it can do that and spit that out. And furthermore, I can stop it in the middle. I can hit Control-C because it's basically got this a visitor pattern where it's going through and printing all that stuff. But anyway, yeah, Chris noticed when I did a dir that he saw FIP in the mix. So that library is indeed being used to pretty print all this stuff.
Cool. Thank you for
no problem.
Thank you for clarifying that.
Yeah. So the analyzer. So I showed you near the top. So when I look at the analyzer, I want to say there's largely maybe like 4 or 5 chunks of stuff in here. Like at the top is a bunch of stuff related to warnings and errors. I'm sorry, I'm scrolling pretty quickly, but here, this whole chunk here is like all the warnings that might appear. And what the strings are that get emitted whenever you whenever you trigger an analysis warning. It'll use this code in this chunk of the analyzer here to form the message that you see in the REPL or in your console when you're compiling. Another big chunk is, let's scroll just through it. And this is the way I see this stuff, is I just kind of I'm trying to explain the lawnmower engine. I just look at the pieces here and I see stuff, and it all means stuff to me at this point. What's the other interesting? There's a few other large chunks in here. I think this is still error stuff. I want to show you a little bit of the type inference stuff, because that's a little bit interesting with respect to type analysis.
Haven't you done a lot of work there, improving type inference?
So if we go, yeah, I did. If you go back, so there is.
Thank you.
Oh, yeah, I did it because it was fun. It really was fun to add some of this. So the by type inference, we have to define these things, what this means. If I say, this exists in other languages too. It's not special to Clojure or ClojureScript. If I say let x equal 1 plus x2, right? It knows that x, this little x down here inside here, it knows that it must be of a numeric type because it was bound to the number 1. And if I were to change this to a string type, I get an analysis error where it says, hey, you're calling plus with something that's not all numbers. The first argument was a string, And the fact that it can tell you that, basically that x is a string being passed in right here, is basically type inference at its core. It basically, you start from root things here that yeah, the number 1 is a number. We can all agree upon that, right? And then anything that you bind it to has to be a number, and it kind of flows. The types flow through the program, and that's part of what the analyzer does. And the analyzer, when it's doing this, you have to say why. Clojure is a very lispy language. It's very lax about types. It's dynamically typed, but yet we have the static analyzer sitting in there. And you might say, well, why? And the answer is it's never there to tell you no. It's not there to say, your program's malformed. Clojure and ClojureScript are not statically typed languages, like C or other, or Fortran or Java. Those languages, if you try to compile some Java code that has a type issue, it just won't compile, right? It'll be a type error and it'll stop. Clojure and ClojureScript are not statically typed. So the type inference that it's doing inside the analyzer is not there to cause your program to fail to compile. It's actually there just for performance reasons. The example I just showed you is perhaps a secondary reason for type information to be in there, is to give you a warning, to kind of give you a clue that your program may be malformed. But the spirit of Lisp and whatnot is that you basically can write a program that's very abstract and very dynamically typed, and that kind of trusts that you know what you're doing, and that your program could perhaps produce an answer even though you can't deduce the types, or it would be very expensive or very hard to figure out the types involved in the program you're writing. But for some simple cases, like this little example here, the analyzer can see the types. And what I mean by loose is if I were to write a function that took an argument, fn at this point, when I write this function, it doesn't really know that x is going to be numeric. So it can't, at this point, it can't produce any warnings because it doesn't know. Now, having said that, I could annotate the types. I could give it a hint, a type hint. I could say, this is string type. Then I've just kind of hinted the compiler. I said, hey, analyzer, this thing here is a string. And then now when it goes to compile this inner type, it now knows. I've given it the information that it didn't know by hinting it. And this is not, like I said, this starts to look like a typed language. It starts to look like, did I just put a type annotation on there? Like in Java, Am I saying that this is a type? Well, really, it's a type hint. It's a hint to the compiler to say, hey, even though you couldn't deduce this through inference, I'm going to hint you. I'm going to tell you what the type is. And then from that, it could do other things that really, I want to argue are there for performance reasons. And the reason I say that, you might ask, well, what is this whole performance thing? The deal is that if you know that things are of a certain type, then the compiler can rely on that information and it can emit code that is more efficient by leveraging the fact that you've told it what the types are or that it inferred what the types are. I can give an example of that, I think.
Does the Google Clojure compiler also have some capacity to do that as well?
It seems to. I know that you can give it type information, and I've messed around with it, and I've never really gotten it to do stuff that I thought was like really optimizing based on types. But I think I've seen evidence of that being in there. So let's see. I want to do. Let's see. Oh, the original reason is probably a good one. If we go back to like, why was type inference even added to the compiler? And it has to do with this thing called checked if that we could talk about really quickly. So if I say foo x if x 1 2. So this program that this small little function I wrote is if I do foo of true should give me 1, right? So it's always difficult for me to know what the audience knows right now, but this little function here, all it's doing is it's saying if this thing happens to be true, then evaluate to the first argument. If this thing happens to be false, then give me the second argument. So it's like it's a tiny little example. This is how if works in Clojure. So this is all cool, but ClojureScript has to compile down to JavaScript. So we're going to look at this part of the lawnmower by turning on verbose mode. I'm going to redefine this function now. Oh God. Okay. So what I wanted to show you is this part up here. Ignore all this. This is all var bloat down here, but this is the important part that I wanted us to focus on. What I did was I defined this function, and we actually, by putting this into verbose mode, I got to see the actual JavaScript that got emitted for this function. Another way to do this is just a trick. Let's say I'm not in verbose mode, but I would like to see that. There is a cool feature. What is the name of the feature? There is a kind of like a configuration variable that I can set to say, hey, print function bodies for me. So if I evaluate foo, I'll see the function body being printed. If this were set to false, you get like a more succinct version of what you see when I evaluate a function. Like a function is a value. So when I evaluate foo has a value, and the REPL has to print something. It has to show something to me. So there's a choice. You can see like this as the way to print this value of this function, or you could say, hey, turn on the verbose mode. Tell me what the function body is. And then when I see it, I can see the code. Unwinding the stack a little bit, the reason I'm showing you this is this little beast right here. So this is JavaScript we're looking at right here. And what it's basically saying is if you ignore this, if we just say if X return 1, otherwise return 2, the problem is JavaScript has some funky, I'll let Chris speak, maybe it's got some funky meanings for what is true and false. Clojure has its own meanings for what true and false are. You know, everything is true except for 2 things. False is false. And does the audience know what the other thing might be in Clojure that's false?
No.
Maybe. Yeah, nil is also false. Yeah. So.
Oh, maybe not.
Oh, I thought someone said no. Maybe someone said no.
I said nil. but
Okay,
it
cool.
evaluated to nil.
That is.
Oh, so
That is
so it
correct.
is false. Yeah. So
Yeah.
if I were to call foo with nil, I get the to branch. Now here's the funny thing. Let's see. I'm going to define another function bar, and I'm going to tell it that this argument is Boolean. Boolean. Okay, so now if I look at bar, the difference now is since I've told the compiler, I've annotated it and hinted it and said, hey, X is going to be a Boolean value. It trusts me. The compiler trusts me, and the JavaScript that it emits doesn't have this little truth thing sitting inside of it. So now if I call bar,
that's very cool.
I'll get this.
Like you can really see how that like.
Now here's the trick. If I call bar with 0, you're going to see the truth of what's going on here. 0 in JavaScript is false, right? It's falsy. I go back to foo, which I didn't annotate, and I pass in 0. This is the correct behavior. In Clojure and in ClojureScript, the number 0 is a truthy value. The only two things that are false are nil and false. So to make foo work properly and return the number 1, that's what this little that's what this CLJS core truth thing is. It basically is it's like dealing with the fact that we're dealing with JavaScript. It's like, okay, when you pass in something like 0, it has to like wrap it with another function to kind of deal with the fact that we're in JavaScript and return the right thing. It's teaching JavaScript ClojureScript's notion of truthy and false. So that's in there. That's in the code you're emitting. But you might say like, oh man, do we have this in everything we're doing? Like evaluation of Booleans and conditionals with ifs is a very like common thing to do when you're programming. It's all over the place, right? You're always evaluating whether or not something's true and false in your code. Well, I don't want to say always, but often, right? Your code is making decisions based on things being true and false. So the very first reason for adding type inference was to try to remove these things where they're not needed. So just like I annotated this as being Boolean, if it can detect that something is a Boolean, it can get rid of this thing. So an example might be, if I just write this simple program here, right? And I look at what gets generated for foo, it basically, the code that's getting emitted is a call to the even function. That's it right here in the JavaScript, right? And the main point is that that little call to CLJS core truth does not exist in the submitted code. And the reason is it knows through type inference that even returns a Boolean value. Therefore, it doesn't have to have this, it doesn't have to have a further wrapping of CLJS core truth. If I were to instead define my own function, let's say, sorry, I can't type. I really can't type my even of x. And I'm just gonna, I don't know, I'm not gonna even define it, right? If I then go back and change this thing here, just to show you what I'm trying to illustrate. Okay. With this function that I defined, my even, the compiler doesn't know what it returns, or maybe it does because it could look at this, but it's not a Boolean value necessarily. So it has to shove this extra thing in there. So the reason for explaining all of this was that type inference was originally added so that the compiler could track and deduce when things are known to be Boolean values. So it could get rid of this little thing right here and make your code a little bit more compact and perhaps a little bit faster, a tiny bit faster. So that was the original type inference. And from there, it's kind of grown to add more and more things that can be used. Like if it knows that things are numbers versus strings, whatnot, you can imagine like the compiler can then leverage that type information to emit more efficient code. And winding back further, all that's done in the analyzer. And it's because types are kind of like closely related to meaning of your code. It's deducing this stuff. So an example of that might be, here's some things where it's basically a bit of code, which we'll look at. This is a kind of a cool one. Let's see, predicate to tag. So here's a little bit of type inference code. I'm not going to explain it in detail. Not that I could right away on the fly, even though I wrote this code. What it's doing is it's basically examples of certain types of type inference, right? So, so here's an example. This is just kind of cool. So if I go back here and I say, string, if X is a string, then perhaps do something with it. Maybe append a string to it, otherwise do something else. Maybe return the number 1. The whole point is, I guess I need to give it a name. Huh? I'll give it foo. The point of this long-winded explanation is I think it's kind of cool. In this branch right here, it knows, because of the fact that the string predicate was satisfied, right? It knows that if it's going down this path of the code, it knows now, because of that X must be a string, because it satisfied the string predicate, right? And where you could see that happen is if I had code that was treating it as if it were a number, right? It now knows, this is kind of cool, I think. The only reason it knows that X right here is a string is because X must have satisfied the string predicate. And that's just an example of type inference. It's predicate induced inference. And I know this is kind of deep in the weeds, but that's exactly what this part of the analyzer is doing right here. It's basically saying, if you satisfy this predicate, then it knows that you must be of type string. So that's going on inside the analyzer, is basically a lot of this kind of, I don't know, mind-bending type inference stuff that's going on. It's looking at your code and trying its best to glean types from stuff, either by seeing that like something was bound to a string or a number, therefore, a literal that has a type that it can deduce, or a predicate's being applied that implies some sort of type. So all that's being done in the analyzer. And you don't need to know any of this stuff. Your code still works. The stuff, all this stuff worked previous to any of this type inference being added. All you're getting now is, like, as we add type inference to the compiler, is that it will give you more warnings at times, but the main reason is for performance. Like, it can basically use that to eliminate code at times, make your code smaller, or make it faster. That's kind of like it's kind of getting a little bit complex when it's doing type inference. That's probably one of the more complex parts of the analyzer, is this type inference stuff that it's doing. But I would offer, let's see, that some of the stuff you can understand. Like, this probably gets closer to the stuff that we probably should be talking about, which is the fact that when it sees an if form, it produces an AST for that if form. That little part that I have highlighted there is kind of like a small bit, and that says, okay, if it sees an if, then the purpose of the analyzer is, it's given a form, and this is breaking apart. A lot of this stuff is complex stuff you haven't learned yet, but it's breaking apart the stuff that's been passed to this if, or it's giving the whole if form. And it's basically like, oh, okay, I'm going to spit out something that says this operation is an if. And that if has a couple of branches in it. That's all it's really doing.
I like lines 1634 and 1636 here. Just because it's very understandable what it's doing. Like we said earlier, that a form can be a list of things, and you look at it and you're like, yeah, that's a list of things, but also, hey, it's a function call, and it has this duality where, like, yeah, it's both of those things at the same time. And so in the case of an if you pass in 5 arguments to an if statement, that doesn't make any sense, right? It doesn't make sense. And so the way, like, it's very readable, like line 1636, if the number of items in the form is greater than 4, then that is just like an error, right? And it really is like no more complicated than that. So
arguably,
again,
the compiler, the only complexity really is that it's an unknown code base to you, and that it's dealing with constructs that themselves might be, the problem domain might be a little bit complex at times, but otherwise, the argument still holds true that you can read this code. I don't know if you can yet, if you've learned enough of, it's like some of these things you haven't learned yet, like this part here, but you'll learn them. Because Clojure is a pretty small language, you will learn this stuff and you'll be able to read this stuff. And a lot of these things that are in here they really aren't that complicated. There is, like, for example, the thing that I showed you where it does predicate induced inference based on the fact that it satisfied the string predicate. That's done right around in here where it says, okay, I'm going to analyze this if, and it's analyzing the then part of the if, right? The thing that happens if the if is true. And inside here, it's analyzing the then branch. But when it does that, it kind of like takes the test that you've passed to it, which is the thing that had, if I go back to here, this is the test. It takes the stuff that it learned from the test and it's passing it down into the then branch. And that's happening, right around here when it's analyzing the then branch. So yeah, this could be difficult to understand if you're like, just, I want to hop in here and look around. But it really is like everything else. It's all understandable in the end. And I'm not trying to convince you that you can go change the compiler and muck with it. But, this hopefully shows you some of the magic that's going on. You can see, like, that little error that I got back there, you now know what's kind of going on, at least,
I'm curious if anybody has any questions or is.
I've got one really quick one, hopefully. I'm really curious the community adoption of type inference, because it kind of feels like the Clojure cell is like dynamic, expressive.
Yes.
And this feels sort of like a TypeScript to JavaScript thing where it's good dev work, but obviously there's a lot of value in the performance that this offers. It feels like something you'd really want to use, but then I could also see the community really not for it. So I'm just curious how it's been adopted.
Okay, so type inference is not, like, it's not part of the definition of the language that's being sold to you. It's not part of the definition of Clojure and ClojureScript. The fact that type inference is going on underneath the hoods is just something it's arguably doing to make things better, but you need not know about it at all, and you don't need to buy into it, or even enjoy it or whatever, or adopt it in any way. It's just there, and you can ignore it, right? And it's only there to, like, make, like, if you started, like, saying, oh, look, this, like, the Scala.js compiler or this other type, they produce code that's this efficient or whatnot, and you start comparing it to ClojureScript and what it emits, you want ClojureScript to be kind of competitive, right? You want it to be able to produce efficient code. So that's kind of like part of what's going on, is this stuff underneath the hood is there, like you said, to make things be more performant. But it's the fact that type inference is going on in there is not something that, like, needs to be, like, bought into by the community or I think that's what you're kind of getting at with that question, in terms of, like, oh, like, you don't need to say, like, oh, you should use this language because it has type inference and it has this, that, and the other. The type inference is kind of, like, definitely very much a thing on the side, Yeah,
I mean, when it was added, like, it didn't, like, I had a bunch of, ClojureScript programs, and, like, I didn't change anything.
Yeah.
I just got the benefit.
Yeah.
Updated the version, got the benefit. That's all I know.
Yeah, and it would be, for example, this program that I showed here, where the analyzer spit out this warning. I think it would be wrong for this program to fail to compile, even though you could argue, like, come on, look at it. It's fundamentally wrong. I want to argue that the definition of Clojure as the language does not include this concept. So if I take this and put it in my Clojure REPL over here, that just compiled. It's not part of the definition of the language, like all this type inference and static stuff, like your IDE, like Cursive might even tell you like, hey, you're doing something wrong here. Or CLJ Condo might come along and say, hey, your program is going to fail at runtime if you do this, you know? And
I guess a bit more like type hinting. Maybe is the wrong terminology, but yeah.
I've seen it used in some libraries.
Type hinting, yeah.
I think I meant more that. Okay, to be honest.
Yeah, I think I'm following you now. Like I want to say you should not be type hinting your programs. That's not part of what is desired in the end. Really, the compiler should do its best to figure things out. And you should really only type hint if you're like in a really tight loop in the center and you need to eke out some performance. And you know that like if you type hint that it'll go faster. And this happens often in Clojure where you have loops and you're trying to get things to be at the same performance that you get out of Java. And you have to resort to type hinting sometimes to get that to occur. And I want to say that that's not part of the spirit of this whole language. You know, it doesn't feel right. This is not a typed language. You don't want to go around and type hint everything and tell it all the types.
Yeah, that's what I was going after.
Yeah, it's definitely, yeah. So even though you saw me type hint back there, that's not part of the game, you know? That's not part of the deal. You can type hint to eke out extra performance, but it's only a thing you can opt into if you really need to or want to.
What happens? Can we go back to the analyzer and say like, I've got my code. I've got the reader produces this tree. I send this tree to the analyzer, and then like what are more what else? Like what's the next step in if it's like an iteration from like my code to the actual JavaScript? What's the next thing that the analyzer is doing? So fundamentally, let's say from the big picture, we now know that the analyzer takes forms and produces ASTs, and you're kind of getting and I think the answer to that will be when we talk about the compiler, the next stage, where it takes that AST and emits JavaScript. So I think what we should probably try to do is see if there's anything else about the analyzer to talk about before we go into the next stage. And I think one thing that's in my mind is the fact that macro expansion occurs in here. That's probably worth, from a big picture talking about. I don't want to get deep into macros because that's come on, macros or, but it's worth pointing, we should at least touch on the fact that that's done at the analysis stage. And I think I've shown you enough of the other stuff. Like I have a list of things that we could go through, but it's not going to add value, I don't think, to your understanding of the analyzer. We could also, I like that idea. I also if in the same way with the reader, if there's just like a list of gotchas, maybe we don't have to go into each one of them, but just say, listen, these 5 things you should know, these happen at the analyzer step. And if you're curious, you could dig deeper. I'm also thinking I'm also thinking about we probably should take another break at some point. So I wonder if we could finish with the analyzer, take a break, and then move to compiler.
Yeah, I think what I would like to do maybe is just touch on the macro part. And then that could take 10 minutes or so. Who knows how these things go. And then I will be satisfied that you will have known enough of the big picture that will be useful to you. And the important thing is this notion that if you take code that involves macros, and so we're going to have to talk a little bit about it. Let's say, I think win is a good macro. Win. If we look at this code here, win true A, that win is basically a thing that says if it's true, you get that. If not, you don't get it, you get nil. Win is a macro. It's a nice macro because it's pretty easy to understand, I guess. I mean, let's just macro expand it.
This is great, by the way. I'm loving this.
So we're basically going to see what this turns into. A lot of the stuff, from the big picture, a lot of code you write is defined in terms of macros. A lot of the core library functions are macros, really. And it's basically a macro, arguably, I'm trying to do this without defining stuff you don't even know yet, but a macro changes fundamentally the stuff you have to work with when you're coding. It's adding to the language, right? Like you can define functions. Functions are things you can call, Macros are things that man, they do kind of like what their name implies. They're macro things that get transformed into something else. So the win macro is kind of like a template or a short way of writing this other thing down here. It turns into something else. And a lot of the stuff you write is actually macros. A lot of the code you write, or is a macro. Quoting this thing. Yeah, and it turns into something else, right? It turns into it's not important what it turns into. What's important also is you can't take the value of a macro. You can't pass. I wanted to say, oh, I want to treat f as an or 1 or 2. And then if I call this, you can't. It's a macro, and there's a fundamental difference between macros and functions. Macros are done at compile time. You can't take one and pass it around at runtime. So this is difficult to do without describing macros in great detail. But the way I kind of describe it is a macro kind of feels like a cookie cutter thing that's like a template that you can use in your code to expand out into something else. You can define your own macros, but most people never do. I hardly ever define macros when I'm writing code. I just use them all the time. You can, if you found that you were writing code that's kind of repetitive and it's doing the same chunks over and over again, you're like, I'm getting tired of writing this boilerplate and they look the same shape. You could, that's an opportunity to say, like, maybe I could write a macro that like generates all this boilerplate given a few arguments, and the parts that remain the same end up in your macro. So in a sense, a macro is kind of like a function that the compiler calls to take a form to then turn it back around and give back another form and expand out into something else. It's kind of a mind-bending thing, and they're very rarely used when you're writing your own code. But the truth is, when you're programming in ClojureScript, a lot of times you're calling macros all the time and all the code you're using, and you don't even know. You just get used to it and you're just using macros left and right. So macros, because they kind of are like recipes for turning code into other code, the analyzer, in order to deduce meanings of things, that one of the first steps it has to do is take your code and macro expand it all out. And in the Focus picture, I wonder if I still have that around. Oh, yeah, good, here it is. He drew it as a tiny little piece right here before analysis. That's kind of appropriate. It's like you put in some code, like this if thing that I have back here. Where did it go? Or the when, I'm sorry. It was here, right? Let's see, when. Here it is, back there. This here that I have highlighted, the if true, and then a do a, this is more fundamental. If is a special form. It's a more fundamental thing. It's something the analyzer can understand and emit. I think I just showed you the AST part for the if when we were back in here. When it parses if, it spits this out, right? So the analyzer, in order to get to that,
okay, can I just want to I want to say what you just said. I just want to say it again.
A different way, yeah. Okay.
So, okay. So if you go back to the code or intelligent. Okay.
Yes.
You've got that's the def method parse for if. Mm-hmm. And again, if you're not, I know that you guys can't read this, but you understand essentially between lines 1632 and 1644, that's responsible for handling if, just right.
When it sees an if, yeah. Mm-hmm.
Yeah, and what Mike is saying is that there's also a when in Clojure, and there is no corresponding def method for when. It doesn't exist. Like you could go search that file and look for it, and it wouldn't be in there because it happens at the if you go to Focus's picture.
Yes.
The when part happens at that yellow block where with a reader generated data structure. Remember that was like the first hour. That macro, then we have macro time, which is, it's like that analogy. I don't know if this is a good analogy, but the analogy I used was you kind of slipping behind the stage and you're, moving the costumes around, or you're in the ceiling and you're moving the puppets around or whatever. It's kind of secret, right? And then it passes it to the analyzer. So it's like you can slip in there and do some little magic if you need to. I can also confirm what Mike said, which is that in day-to-day of writing programs, you just never need to write macros. But it's a really amazing. I'm really glad they exist, because I use libraries that are written in macros all the time, constantly.
Yeah.
And but you don't have to think about it. It's just there. I don't know. It just works, basically. I don't know.
Yeah. And macros.
Here's sort of my question of, I hear this dichotomy all the time of, list is so wonderful because macros let you do all these things. But then the next sentence is, but I never use macros.
Yeah. Yeah. So there's like the whole Paul Graham camp, macros, like growing a language by defining macros and building up a language to solve your problem, right? That mentality, I don't think I buy into that. I just use the core library function, or the stuff that's in Clojure core. I use the macros to solve my problems. Like, for example, I'm still like in 3rd grade using English that I knew back then, and I'm communicating in that like primitive form. I'm not like developing big words to talk about things later on in life. And Paul Graham is smarter than me. He's like, he argues you should like build up a language using macros to then go and solve a problem. It's almost like building a domain specific language to solve a problem by approaching a certain problem by defining macros to do it. And that's happened sometimes. Like there's certain libraries, like I think like Core Match, Core Logic. There's libraries out there that are kind of like, or Spec itself. Spec is heavily macro influenced. A lot of these libraries, they kind of like add new fundamental things that are like just fundamental in a sense, and they are very driven by macros. But that I fall on the other side of that dichotomy of what you say, like I just use the stuff, I define functions. And there's maybe another way of saying that is like you'll see another argument that says that data is greater than functions, which is greater than macros in their value. Data is fundamental, right? Data is the thing that's like the fact that we can take a vector and put it into a REPL and pass it around. That is the good thing for this camp of people, right? And then if you could say, if I compare that, data is much better than giving me a function, because that function is like opaque. I can't see it. I can call it, but I can't easily paste it into a REPL. And then macros are even worse. You can't even take the value of a macro. It's just there and it expands. So there's like 2 different ways of looking at all this stuff. And I think the macro thing is very intellectually stimulating. It's very geeky, but I fall on the other side of all that.
Yeah. So another thing, or like when somebody says like, don't use macros, they're not saying never use them ever. That's not what they're saying. They're saying for 99% of programming, they're probably unnecessary, and they're not the concept you need to solve the problem. But 99% is not 100%. And oh my gosh, am I glad that 1% is there, because it allows changing of the language at like Mike is saying, like a very low level that can be incredibly powerful. So I think I've got maybe two ideas here that are one is that the core async did not exist in ClojureScript when it was first released, I believe. And then it was added to the language later. And I'm pretty sure that core async is a bunch of macros. Is that right, Mike?
It is the mother of core async has a Go macro in it. It is the biggest, nastiest macro you've ever seen. Yeah, it is very macro.
So compare this. So we could talk about core sync. We're going to talk about core async in the future, but essentially it allows for asynchronous programming that looks synchronous. Like it appears to be synchronous, but in reality, under the hood, it's asynchronous. It's a
fundamental change, yeah.
And I want to compare that. So I love to compare core async in ClojureScript to async await in JavaScript. And Pat, I know you're like a C programmer, so you may not be familiar with that. But in JavaScript, the actual JavaScript language is evolving and growing over the last several years. Mm-hmm. And one of the things that was added to the language was a new keyword called or 2 keywords called async await. And they effectively do that same thing. They make code that looks synchronous. Under the hood, it's actually being asynchronous. But it required an actual language change. Like the ECMAScript committee had to do a proposal and like review the proposal and then
wait
get the
3 years.
proposal
Yeah.
and then wait 3 to 4 years. And now there's maybe browser support. I mean, we're like literally changing the language, right? In ClojureScript land, we just added a macro library. Boom.
Yeah.
Right. We got it overnight, essentially. Right.
And
that's
along
that
with
power. It's that power. Yeah.
Along with that theme is that in order to quote change the language by adding macros, you're never changing the surface syntax of it. It's always forms. You don't have to add new syntax. That's not part of the game. Like the
compiler didn't change. The compiler didn't change.
Right.
Yeah.
And so fundamentally, you can, because of this fact that you can use a macro, you can, you're not changing the syntax, but you are adding something to the language that you have, which is like some new construct that will expand into some new thing that you couldn't do before. And you can do that yourself. Yeah. That's very much a true thing about macros. And one other thing I'd say about macros is that they sometimes are hard to understand. And I think it's an example of something that is difficult to understand because they are so simple. It's an example of that thing where like it's hard to get because it is so simple that your mind is like trying to look for some other explanation. And really, it is not complex at all. And it really is just a function that is called by the compiler to take a form and turn it into another form. It's nothing more than that, no magic. And people will go around the wheel trying to understand and be mystified by macros. And the difficulty lies in the fact that they are so simple. And that's why they're hard to understand. It's just because of how raw and fundamental and simple they are.
I have another analogy, but I don't really know if we need it, but I'm going to throw it out there. So you can think of macros like the legal system. Let me explain. You're like, what are you talking about? So like I live in the United States, like most, there's courts, there's judges and juries, there's lawyers, there's laws, there's legislators, there's this whole sort of legal system. And I don't work in the legal system. Like I'm not a lawyer, right? And so I don't have to interact with that system on like a day-to-day basis. Maybe occasionally I have jury duty or like, oh, I got into a car accident. I have to like go to court or something like that. Occasionally I may have to interface with it, but I don't really need to know it in detail. Like I don't need to know the depths of it. It kind of just happens over there. Now, it's kind of like I'm saying that like the legal system is macros. Now there are like a lawyer or a judge, they're living in the world of macros like constantly. And I'm sure that there are some like Clojure programmers that kind of like live in macro land all the time. But the vast majority of people, or saying like programmers in this analogy, it's there occasionally, or it's there, they like benefit from the externalities of it. Occasionally they may have to interface with it, but for like the majority of your day-to-day life, it doesn't impact you, right? But you get a benefit from it, like almost implicitly.
So what I wanted to just show you on the subject to perhaps make it less mysterious to you is show you that one small piece of the lawnmower engine that makes it work. And you'll be like, it is like Mike's saying, it really is just a function called by the compiler. It really is nothing more than that. And that is in, let's see, right around in here. So here inside the analyzer, remember we said if you pass it a when, it's got to expand that into the if ultimately so that it can make sense of it. And inside the analyzer, it's making use of this macro expand one function here. And right here, right around here, it does, let's see. Well, here it's trying to find that function that I'm saying, like, okay, it's trying to, like, it sees the symbol when, and it's like, I need to get the actual code that implements when that will expand out. So right here, it's like, it's getting the quote expander function. It's getting the actual when macro. And it gets that, it's a var, it gets it, it's got it. And then right here, where is it? I lost it. It was so simple. Macvar, there it is right there. There. That part I have highlighted there is the magic. It's basically, it's got the macro and it's applying that macro to the form, right? That's all a macro is. It's inside the analyzer. It's like, it's, in this case, when is this macro var. It applies when to the form that was, basically the stuff inside there. And it expands out into this if. And that's, and that's what form prime is. It's kind of an iterative thing. Like you may think, oh, a macro could expand into other macros and you could go down. It's like this turtles analogy, right? So it takes, it takes it and expands it to a form prime. And then it checks to see, did form change somewhere here? I think it compares at some point and it keeps going until it sees no more macros. But that was the main thing I wanted to show you, is that macro expansion has to happen inside the analyzer, because it needs to do that in order to analyze. And Focus's picture is good. The yellow block is kind of like, it's kind of like prior to a lot of the AST being generated. And it really is no more mysterious than that. That's the one little thing right there.
I love that. That line of code is the yellow block.
Basically.
Yes.
Yeah.
That
It
line
is.
of code
It
is
isn't that
responsible
complicated.
for so much power, basically.
And hopefully if you're like struggling with macros a year from now and you're like, oh man, maybe you'll remember back to this and you're like, it really just is a function called by the compiler at compile time or analysis time, because analysis is part of compile, and it's just being called while the code's being compiled to expand it out in order to generate the stuff that's going to be analyzed. It is no more complicated than that. The syntax for writing macros is weird and funky. A lot of stuff is funky, but the idea is very simple. It's just a function the compiler calls to produce more code that can then be compiled. With that, I think there's other things we could talk about in the analyzer, but I don't think it's worth it. I think it's, I think you all have like the main gist of what the analyzer does.
Yeah, I think we need a break too, I think.
Yeah.
So, okay, awesome. So break, and then what comes after the break?
Pretty much the emission part.
Emission part.
And to be honest, the Google Clojure part is going to be almost nothing compared to any of this, because there's not much that we do. So the emission part is pretty simple. So I estimate after this, maybe half an hour, hopefully. We might be out of this. Yeah.
Very cool. Yeah, this is a long session. Let's take a break, y'all.
Can I ask one quick question?
Please, yes.
Yeah. So I know, so you mentioned so this might be like my misunderstanding, but it seemed like a little bit of a chicken and egg issue, because the win macro calls if, but then in the if definition, it used the win macro.
Yeah, let's see. Oh man.
I think that might be just a slight, you may be like
right
said
here
that slightly incorrectly. Yeah. So that code, well, I'll let you answer that, Mike. Yeah.
Well, so first of all, this is Clojure code you're looking at here in a sense, but it compiles to ClojureScript. So I can't make that argument. This can be ClojureScript code that's running in self-hosted. I want to say that when this gets compiled, all that stuff is there. There is some sort of circularity sometimes in some of this stuff, and it all just works out in the end. Let's see if I can give you a satisfying answer to that.
Yeah, I don't like that.
Yeah.
So that okay. What you're looking at, these win calls in this is the analyzer that this is running as the analyzer. So when that win call happens in this analyzer at runtime, it's not doing the thing where it calls itself, if that makes sense. So you're saying that win expands to if, and then if contains win, but these are in two separate contexts. Does that sort of make sense?
I think the chain gets broken somewhere in there. Yeah.
Okay.
Yeah. It's not. So it does that. Okay. That right there, that def method, when this runs in the analyzer, it is not running in the same runtime context as
the REPL.
Correct.
Okay.
Yeah, these are like separate sort of contexts, and that's why it's not recursive. Like that win in there is not recursive to. It's a difference between the code that's the analysis that the analyzer is doing and the running of the analyzer. These are separate contexts.
Yeah, that makes sense.
Okay. It's a good question though, or it's a great question.
Yeah.
I would say.
There's other things like that, like the fact that persistent vectors are implemented in ClojureScript itself, but yet the persistent vector code, if you look, you start to wonder, are any vectors being used inside there? And I think the answer is no. But these kind of things can happen. There could be some recursion in some of that stuff, and you have to break the chain somewhere. And sometimes working on this stuff, you find that you caused a loop, and you're like, I did something, but most of the time it doesn't happen. And always the answer is always there if you dig deep enough. Yeah, I know that's not a satisfying answer. I think Chris gave a better answer. That's a great question, though.
Yeah. Okay, more questions or ready for break? And I'll pause the video for the future YouTubers. Hello, future YouTube viewer. We're glad you're here.
Welcome.
Yeah, welcome. Okay, I'll pause.
Cool.
Okay, and we're back. And so we took a break and we're done with the analyzer. And the next step is it's the compiler phase, right, Mike?
That's what it's called. Yes.
Okay, so it's called.
It's a weird name because we're talking about the compiler, but yet there's this little piece in there called the compiler. Focus's diagram calls it the emitter, I think. Let me go back to his. Emission. Yeah, that's probably a better name for it. And its job, so if we like recap where we are, we take strings and we read them into forms. We do a little macro expansion stuff. We take those forms that occur after you've macro expanded everything out to its, special forms or nth degree things. Then you analyze them to produce this AST, which is a rich, meaningful structure that tells you like what the code is, what its meaning is. And now our job is to ultimately produce JavaScript. I think, so the emitter does spit out JavaScript directly. It's almost vulgar. It spits out strings. I think David Nolan had some other ideas of perhaps improving that at some point in the future, maybe to spit out something else, some sort of like abstract representation of JavaScript so that other tooling could work on it. But the way it is now, it's very simple. It spits out strings. I think if we looked at the if stuff, because that's what we were focused on before, we were looking at parsing of if.
We did already see a little bit of this when you were kind of, that trick you did where you said like show function bodies. So we've already seen like a hint of this already.
Yeah. So, yeah, you might at this point, you might think, wow, we have this AST that's this rich, meaningful thing. You would think, oh, now my task is to convert this into JavaScript. That's got to be horrifically complicated. How can we possibly do this given, we're basically like taking something that has meaning and producing another language, spitting out another language from it. And I think part of the reason it's easier than you might think is that JavaScript itself is pretty powerful. It's got certain constructs in it. And it just makes it easier. I would imagine that like the way Clojure works, it's spitting out bytecode at that point. So it's probably, I honestly don't know, but I would imagine it may have a tougher job at this part of it. Whereas ClojureScript, just spitting out into another language that's, close enough to the same level where it's like, yeah, it can do it. And if we look at if, you'll see that that's clearly the case. So the AST for if was just kind of like what you'd imagine. It's just got some of the stuff in it, like the test, the then and the else, whatnot. So our job now is to take this abstract stuff and spit out some JavaScript code. So if we go to the compiler namespace, let's see. So I want to look for, there we go, right here. Found it. Okay. So there's a bunch of different handlers for the different special forms and whatnot to spit out JavaScript code for the different things. And if this is the code for if. So what I want to show to help understand this, let's go back to the REPL. Let's see. So let me put this in verbose mode. If we do if, that's not a good one because it evaluated it. Okay, so this is the JavaScript right here that got emitted for this ClojureScript, and it is actually a ternary expression in JavaScript. But you say that doesn't look like an if. If we instead do, let's see, can we get it to do it this way? Yeah, okay. So I just slightly changed things a little bit, and what I did was I caught this here is kind of an expression. It's kind of an expression place, whereas at the end of a do, it turns into a statement context, if you will. And it just, if you think about the way if works, in Lisp in general, if is a form that evaluates to one of its two branches, right? In JavaScript, that's not true, you know, or in Java and a lot of these other languages, if is done some, you know, if is kind of like a path, or what I want to say, what's it called? You're controlling flow of your program, and you're making it go down one branch, and then it might execute this block of code versus the other block. And those blocks may have different side effects, but it doesn't return the value of those blocks in typical languages like Java and JavaScript. Whereas if returns the value that you evaluated, that, you know, returns either the 2 or the 3 in this case, but that construct is very close to this ternary expression that exists in Java and JavaScript and C. So that, I don't know if you haven't seen this thing, the way this works in JavaScript and Java and C is that you have like a test. I'm just going to type it here and have a test, and you have a question mark, and then you have the 2 values that you could get, you know, 1 or 2, and you put a colon between them. That thing there is kind of like an expression that represents the result of, you know, looking at this test and then picking one of those 2 other expressions. So the ternary operator in JavaScript is pretty much the same thing as the if expression in ClojureScript and in Clojure. As a matter of fact, when I go back to programming in Java and I don't program in JavaScript, but if I go back to Java or C or whatnot, I find myself liking to use these ternary expressions because they are very functional in a sense. You evaluate them and they result in the value is the thing that you get out of it. So there is two different manifestations you can get out of this, though. You can either get this like kind of this ternary thing if it's just by itself as an expression, or if it's like in statement form at the very end of a thing, the whole thing is going to evaluate or return, you know, it basically is returning it. What this does is it basically encloses everything inside of a function, and it returns, it calls that function directly. I think there's a name for this in JavaScript. Is it immediately invoked function?
Yeah, an immediately invoked function expression.
And this ifs are kind of useful things, and the compiler will emit things as ifs all over the place to get it to, like, I think the way let works might involve ifs. Let's just see.
I'll put a link to that in the chat, by the way, guys, an iffy.
There's an iffy right there sitting in there. So you can see how the compiler implements the idea of a let by saying, oh, okay, we have to do a binding right here. We have to set x to 1. So what it chooses to do is it says, we're going to do it by making a var inside of a function and setting it. And then making an iffy that, like, this little part down here that evaluates this is what it's going to return. And then it immediately calls it because this whole thing has to evaluate to the thing that's in there. So to implement that is pretty straightforward. If we go back to here, so we have an AST coming in, and this pulls apart the pieces that are in that AST, and we get the bits of it. And it's basically saying, hey, if we're in expression context, then just, you know, spit out the string. You know, this is kind of vulgar. It's spitting out the JavaScript right here. It's saying, hey, this is what you kind of expect is, like, it is emitting the JavaScript at this point. It's basically saying, okay, I need to do this. And this truth thing, let's see. Remember we talked about that earlier. There's a way, let's see, in one of these branches. Oh, if you're not checked, I guess in this branch down here, that's it right there. It's eliminating that truth check, depending on which of these 2 branches it's going down. So that's an example of how the type inference way back when is used ultimately for a performance enhancement in terms of reducing code size and making it run a little bit faster. But I think you can probably
that's super cool to
read this
to see the finality of that, or because we saw that earlier, but now we're like seeing the other end of the rope.
Yeah, and so just like there were in the analyzer, there was all these def method parse if and various kind of like the special forms essentially of the language, all the like bottom atomic things that you might get down to. In the emitter, there's the same thing, or in the compiler, there's similarly handlers for each one of these things. And all it's got to do is spit out the code. Here, case, if we look at case really quickly, inside here, the only thing I want to show you is, so case is basically kind of like a fancy if, you know, with different multiple branches, maybe you can think of it that way. But what's kind of cool is under certain conditions, it will emit a switch in JavaScript, which is a much faster, highly performant way of like branching to get to the right spot. But it can only do that in certain constructs. You know, if all the things are in a case, basically all the things have to be in the same type, so it can actually emit JavaScript that works this way. I think like if you have a case on all strings, you're good. It can emit a switch. But if you have a case that involves maybe strings and other things mixed in, then you can't get away with implementing that as a switch in JavaScript. That's just an example. You know, it's like the emitter will try to emit the most efficient code that it can based on the meaning of what's in the ASD.
This might be a JavaScript question, but do you know if and case are any different at the JS runtime level? Like if I had a bunch of if else, or I had a case.
Oh, okay.
And it's like,
right.
this is not really a Clojure question. It's
right.
Just, yeah. I'm just curious. Yeah.
Yes. So the way I would answer that is from what I've seen, like from optimizing stuff, like if you take the output that this emits and you're trying to optimize the ClojureScript compiler itself in terms of making it generate more efficient code, what you have to often do is try something and try it in all these different JavaScript VMs. And they will oftentimes be, some of them are clever and they could do anything, right? They could take like, I would argue it could take the if else, and turn it into a straight case lookup, like a switch, basically, depending on how clever that. And in each of these JavaScript VMs, some of them are more clever than others, and you know, they're all some of them are more mature and they'll emit things in more efficient ways.
That's what I was thinking, because I was thinking, well, so you have an opportunity here to optimize for the JavaScript that ClojureScript is emitting. But then the JavaScript engine has like its own opportunity to optimize, and like, we're not really in control of that. Like the team behind V8 might make some sort of change that actually is not in the favor of whatever. So
that's a good point. Yeah. So yes, the optimizations that you apply here are so far removed from reality that you can only do so much. And then to truly like say like we want to make a change to the ClojureScript compiler, and we're like, hey, this will make things faster. And the way you argue that is you have to actually involve the Clojure compiler, because it's going to make its own. So you have to compile things under the advanced mode, which involves using Google Clojure to like let it apply its optimizations and whatever transformations it's going to go to do the code. And then you have to run it across a bunch of different JavaScript VMs and see if it speeds up on all of them and maybe slows down on one. And the only way to do it is to actually have empirical evidence that some particular change will. And sometimes it's huge. Like you'll make a change that like things will be so much faster. And I'll show you that. I'll show you one. That's another interesting thing, which is this idea of a compiler intrinsic, which is kind of a very geeky, intellectual kind of thing. And what it means is when you write code, and this is not just specific to Clojure and ClojureScript, the compiler can say, aha, I know what you've just did. I know I'm going to take the code that you wrote, and I'm going to do what I know is better. It's an intrinsic, it's built into the compiler. It's going to say, I'm going to ignore what you actually asked me to do, and I'm going to do something else. And there's actually two places where this occurs. One is back in the analyzer. You can set certain vars, like you can say, I think they're near the top of the analyzer. Flip back there real quick, just because this is a cool subject, and we're almost done. So this is rounding out this stuff. There are a few things here. You can say set warn on a reflection, or you can set unchecked if or unchecked array, various things that control the compilation itself. You put these typically at the top of your file. If you say set warn on reflection, right? So backing up a little bit, let me go back to my, come on computer, trying to get back to my REPL. Remember we did set before for a thing.
These function bodies.
Yeah, so when I did that, by doing that, I'm actually changing a value in the runtime state to something else. There's a value, a box that's holding a value that's now set to true in the runtime state. But other things like By doing this, I guess I got the wrong one. What was it named? Oh, maybe this is only in regular ClojureScript. Yeah, it's not in self-hosted.
Clojure, right?
Yeah, yeah. This is an example of that conditional stuff. But the point is still the same that I'm trying to make, is that when you do these kind of things, these actually change the way the compiler behaves. And in Clojure, because in Clojure, everything's all in one ball of wax. You can set things and it's like the compiler's there too, and it can like deal with things. In ClojureScript, when you set something at the top of a file, it basically has to, it's an intrinsic. The compiler sees that. And down, let's see, down near the bottom, here they are, right here. These are kind of like the intrinsics for the set primitive. And it basically says, oh, okay, you told me to do something here. And it's like, thank you. I'm not really like, I'm not changing some runtime state in the browser in the end. I'm actually changing the way the compiler behaves while it's compiling. So it grabs onto these like hooks that it grabs, and they're intrinsics in the analyzer that says, okay, I'm going to now change the way the analyzer behaves for the rest of this file as it's analyzing down. So it's changed some state in the analyzer. So it's like a weird use of set. It's like almost abusing it, really. You're saying, I'm going to use set to set something that really is changing the analyzer as it's running. And I think this happens because it kind of came from Clojure, where everything is balled together in one big thing. So that's an example at a high level. That's an example of an intrinsic in the analyzer. Basically, it's saying, okay, I see you just set a certain var that I know about. It's a var that I know as the analyzer. I'm gonna ignore what you asked me to do, and I'm gonna do something else. I might actually set the value, but I'm gonna do something weird based on that. There's probably a better intrinsic that you might like in the emitter, in the compiler. Let's see, that would be, what is the name of this variable? I had a note for myself. Op count. Let's see, am I in the right file? Why is it not hitting that? Let's see, in the right file? Oh, I might be in the wrong. That's odd. This is bothering me that I can't find this.
I don't want to distract you, but I thought of a question, which is roughly speaking, how many of those emit methods are there? Like, it looks like it's a def method.
Oh yeah, roughly it's like the number of special forms, so about a dozen or so.
So, but yeah, so I wanted to kind of call that out, which is just, if you think about these steps, right? Text file, analyzer, macro opportunity to shake it up. Excuse me, I said reader, but I said analyzer, but I meant reader. Macro ability to shake it up, analyzer. And by the time we get to this compiler, or like emitter, I think is a good term for it, there's only about a dozen ways in which the compiler is going to be like writing JavaScript. So only about a dozen. And that's not like a lot, like a dozen is not 137, right? Like there's only like a handful of possible final outcomes. I just wanted to kind of call that out as being kind of a cool thing.
Yeah, it's part of what makes it possible to pull this off in just a few thousand lines of code, or 1,000 or so. Yeah. They are all kind of tied to the primitive things that you might have in a language, like doing an if or a case, or yeah. Okay, so I found the thing that I was struggling to find. It's called opt count, and it's just cool to show as a high-level example of an intrinsic that it kind of exhibits the things that the emitter can do. If you accept that it fundamentally works, right? It can emit JavaScript, like we showed you with if. This is a thing that it can do to make things faster and better. and it's like a hook that you can imagine. So let's go back to here. And if I say def in foo, okay, so count is a function that will tell you how many things are in a collection or in a string. Or so if I say foo of ABC, we should get back 3. Yes, we do. Okay. So the idea of the intrinsic is if it knew that X was a string, in JavaScript, there's a faster way to do this than to call the count function on it. In JavaScript, if you know that something's a string, you could just skip to the end and say, I want to get the length of that string, right? So if I turn on verbose mode, you can see what that last little bit is. In JavaScript, so this is syntax you may not know yet, but it's basically accessing the field of a value. So this is, if you know JavaScript, that's the way you could get the length of a string is you just access the length property of the string. That's what it's called in JavaScript, right? So the compiler has an opportunity for optimization here. When I define foo, if it were to know somehow through type inference or whatever, that X is actually a string, then it can emit a bit of code that's even more efficient. And it's kind of an intrinsic. It's going to say, I'm going to ignore the fact that you asked me to actually call the count function. It's going to instead emit code that accesses the length directly. So if you do right, we'll cause a little bit of inference, type inference to occur, so that it now knows that string or X has to be a string in that branch there. So what it did, ignore all this stuff down here. This is the cool bit right here. It knows if X is going to be a string, then it can just directly access the length field of this thing that you passed in. And it turns out that this is more than an order of magnitude faster. It's like 1,000 times faster, right? Because calling the count function is like a whole nother, if you look at, count is another whole function that like has branches in it that says, oh, let me check this first. Oh, is it an array? Oh, is it a string? It goes down the line, and it finally, then it's like, okay, then it finally gets to the good bit, right? Where it just accesses the length. So this ability to do intrinsics at compiler emission time based on type inference is kind of cool. I like it, and it's basically an example where if we go back and look at how it actually does that, this is the part of the compiler that's taking care of invocations of things, function calls. It's saying, okay, you've asked me to, like the AST, one of the things that you can get out of the AST is a form that is a function call or an invocation. And it can say, okay, you're asking me to, the actual thing that I'm actually calling is the count function, right? And furthermore, it's not just, the thing in the operator position is not just count. The first argument is of type string or array. This same thing I'm talking about works on arrays as well. Array has a length property. So this is an intrinsic that says, okay, if this condition is true, if the thing in operator condition is called a count, and it has to be the CLJS core count. It can't be like a count that you defined in your own program, right? This is only applicable to the real count function that's in core. Then this thing is, this let bound thing here is set to true, and then it's used further down, right around here. Here's where it basically says, okay, if that's true, I'm going to emit a call to the length. So that's just an example of the kinds of things that the emitter can do based on type inference and how it can try to emit very efficient code based on stuff that it knows, right? But fundamentally, that's all the emitter is doing is taking the AST and emitting code that implements the semantics of what's in that AST. With things like let, as you can see, it has to do little ifs to like come up with the idea. I think in new JavaScripts, there's a let construct in Java. I don't know JavaScript, but I think they're adding the idea of let to JavaScript.
Yeah. Let's.
Okay.
Yeah.
So that's an example where if ClojureScript was targeting the newer JavaScript, it could just perhaps just use let directly, right? The let that's built into JavaScript. But this targets older JavaScripts prior to that, so it just uses an iffy to pull it off. So that's roughly the emitter really is much smaller. You know, I think we talked about the sizes earlier on, but 2,000 lines of code or so. That's all it's doing, is just basically doing something that might sound horrifically complex, but I think it's made easy because JavaScript has enough constructs in it and it has ifs and whatnot that you can like basically implement the semantics that the Clojure language has in JavaScript. So from the big picture, we kind of like, we have these forms that are pretty compact that you type in your code, you read them, and then you expand out into this huge AST that's rich in meaning, and you collapse back down into small JavaScript again. And the huge AST is gigantic because it's so rich with information that you can then use it when you're emitting stuff. So this is kind of like the other end of that funnel where it comes back in.
What is, I'm seeing Goog dot, what is all that about?
Okay, so ultimately the last stage that we don't need to really talk about in great detail, but it basically takes all of this stuff and it passes it to the Google Clojure compiler optionally if you set things to advanced. But so the Clojure compiler, it's basically a Java minifier, right? It basically, or JavaScript minifier. Its main purpose in life is to make it so that you can write JavaScript that then targets the web, and the resulting artifact that you're putting out there is really small. But the Google compiler, in addition to being a minifier, also has its own runtime and its own idea of namespaces, actually. So the way namespaces are implemented in ClojureScript is basically leveraging Google Clojure's way of doing it, which basically involves, it's pretty straightforward. If you go into foobar namespace, here's a little call to Goog, but what it ends up being is it basically ends up being a nested set of JavaScript objects where like I have an outermost global foo object. And then inside of that is a bar object. And inside of that is my def A, which has a value of 3. So that's just maybe a short way of saying that is the way the ClojureScript compiler implements the notion of namespaces is to leverage Google Clojure to do that. But really all that ends up really being is, at least in the REPL, at REPL time, it ends up being nested JavaScript objects where, one thing is inside the other, nested dolls. But then when you go to apply Google Clojure optimization to all this stuff, it takes these nested sets of objects and it turns them into like compact strings that represent the stuff directly. And it does all types of funky stuff to make it really fast. So like when you're accessing, if I'm accessing foobar A, what really has to happen down at the JavaScript level is it has to do several dereferences, right? To get all the way down there. It has to start at the top level, that topmost object, and then dereference it with bar, and then dereference it with A. Google Clojure takes this and it dispenses with a lot of this and just turns it into a single symbol. Like, you might have a namespace that has lots of parts. It just gets rid of all that, and you just have like a single symbol that represents that. So Goog is also, it's like the runtime library underneath all this stuff. Like if you imagine the way, it's just like a lot of extra nice facilities and functions that you can call from ClojureScript. You can always be guaranteed that they're there because ClojureScript sits on top of Google Clojure. So Google Clojure, if I back up a little bit, half of it is this optimizing compiler minifier construct, that takes your code and minifies it. But there's also the Clojure library that has all these nice runtime functions. So oftentimes you might say, oh, I want to do something in ClojureScript. And you start to think, oh, it's not in ClojureScript core. Like maybe you're trying to do something funny, like you're trying to do base 64 encoding, for example. And you might say, oh, let me go try to find a library that does that, base 64 encoding. And oftentimes you'll find that that's actually already built into Google Clojure. It's like the runtime library is there, and it's directly there for use.
The way I explained this on Thursday night was that you write your program in ClojureScript, and the output of the ClojureScript compiler is like a very large JavaScript program that is written as if it were a Google Clojure like program. And then that gets sent to the compiler, and then the Google Clojure compiler, and then it rips out all of the code that you didn't use. And I sort of demonstrated that briefly on Thursday, and showed how aggressive it is about inlining things and dead code removal.
Yes. Yeah.
So,
it's fair to say that like the Google Clojure compiler wants the JavaScript to kind of be written in a certain way, right? You have to abide by certain constraints. And the ClojureScript compiler does indeed abide by all those constraints. So that stuff can, and the benefit you get is your code is just wickedly fast, and like you showed them, dead code goes away, and
very small outputs too. I'm always amazed at, like, I mean, my current company, we have large programs. The final output, it's like 264 kilobytes. It's like, I cannot believe that all this stuff goes down to 264 kilobytes. But,
and what I found is also, you might find interesting, is that there is, even after having done that, there's more code that's theoretically dead, in the sense that it never does get ever called. But the Clojure compiler itself can't see that, because it's so some parts of the stuff is dynamic, and you can only see that at runtime, that it's never called. So there's other things in there that, like, you could even further get rid of. And that started to matter to me when I was trying to get ClojureScript to fit on microprocessors. Like, you're trying to get rid of every last thing. So Google Clojure is awesome. It will take something and compress it way down to, some tiny thing. But in truth, really, there's like less stuff that's actually called. You can compress it down even further if you knew at runtime somehow to get rid of more of that stuff. So there's one more thing I wanted to say about this stuff that's kind of like the big picture stuff, is that we have this pipeline that we talked about all the way down the chain. And you might think, oh, the reader then takes stuff and it spits out things, and then that goes into the analyzer, and then the analyzer spits out things, and it goes down the chain, right? And in fact, things are kind of reversed in a sense. It's kind of like I would argue maybe like a pull model, where if you look at the top of each file in Clojure, you define what you depend on, right? You say, I depend on this thing, right? So if you go all the way down to the compiler, the Clojure, which is one I haven't showed you yet, but we're not going to talk about it too much. Clojure is basically, at a high level, this is the last thing in that chain of things. And it's basically just taking the stuff and passing it to Google Clojure. It's the end of the chain. But the main thing is this thing here, this namespace, Google Clojure, it depends on the compiler, right? And then if you go to the compiler depends on the analyzer. And then the analyzer depends on tools reader right there. And it's basically just kind of reverse of what you might think, in terms of, like, you won't see in tools reader, it doesn't depend on the analyzer. It's not, the dependencies can't go in that direction, actually, because this is a separate library. But it kind of like pulls things through. And because of that, if you're looking like, how does this thing really work? How does it all hook together? Because you don't see, like I showed you in the analyzer, I showed you a part at the bottom where it's like looping through all the forms. And you might say, where did that come from? What gave it the forms? Where did they get in there? The answer to that is, if you go all the way to Clojure, this namespace, which ostensibly is just all about calling the Google Clojure compiler. There's a bit of code here. I'm scrolling pretty quickly, but it's basically getting ready to call the Google Clojure compiler with your JavaScript code. Below that stuff, where it's calling the Google Clojure compiler, there's a bunch of stuff down here near the bottom where it's kind of like glue code stuff that's like dealing with getting files off the file system, and then ultimately saying, hey, I've got a file I need to compile. And it's the thing that's driving all of this. And basically saying, hey, compiler, please compile us, analyzer, please analyze it. So it's being driven from this end, which is kind of, it feels backwards, but that's the way it is. And in here, while I'm at it,
that actually makes perfect sense to me, that order of operations, like,
cool,
from the file to the, but I'm also very used to, like, ClojureScript namespaces and like the way in which those generally get to be required. And so this is like,
okay, yeah. Down here, one point I would make is the compiler can compile things in parallel, multiple threads. So let's say you have a project that has 100 files and you have a big hunking computer with lots of cores. The compilation of all that stuff can be spread across those cores. And I think you could see like speed ups of up to like 5 or 6 or 7 if you're lucky. So it's not gigantic, but at a certain point it hits a limit where it can't go any faster. So there is an option you can pass to the compiler to make compile things in a parallel way. And you can get a little speed benefit out of it. And all it's really doing here is it's being, like I said, it's being driven from this end. I'm showing you something that's inside the Clojure namespace, the stuff at the end of this chain. And it's basically, it's seeing how many processors you have. And then it basically, what it really does at that point is it looks at all your files in your tree or all of your source files. And it basically just parses the NS forms at the top of each of them. And it looks for their dependencies, right? The NS form of any file, if I go to the top, the NS form is basically listing all the namespaces that this namespace depends upon, right? So I know for me, like learning namespaces, I didn't learn them until like 4 or 5 months into learning Clojure, what namespaces even really were. But effectively, each namespace declares the other namespaces that it depends on. So you can imagine if you have a whole huge tree of files in your project, you can glean like that graph, if you will, by just looking at only the namespace forms. So what the compiler does is it actually, like if you're setting things up, it will look at all the namespace forms in all your files, and it'll find out the order that they have to be compiled in based on this graph, this dependency graph, and it'll go out to the leaves and compile those first. And if you have parallel compilation turned on, it'll do those in parallel where it can, and then it joins up, and ultimately you get a speed up in your compilation. And one thing, you probably won't run into this, but if you have like a project that's really slow to compile, it just because of the way the compiler is implemented right now, you would benefit by having lots of small files, lots of small namespaces, because they're each eligible to be compiled separately, as opposed to like one gigantic single namespace that had everything, all your code in that one namespace, because you can't parallel it. Well, the compiler doesn't parallelize that right now. It's basically just one pass through it.
It took me a while to learn namespaces too. Like when I was first learning it, it would have benefited me to have like a mentor explain how they worked, but I just had to like figure it out on my own.
Yeah, if you're just learning this stuff, you tend to hop into a REPL and you just start typing in forms and evaluate them. You don't need to worry about namespaces, and that's all cool. And then when you're like working on a project, one of the challenges with namespaces is that there's a lot of options that you can pass to the namespace form that really aren't even relevant anymore. In a lot of documentation, you might see like namespaces, like anything else, they end up being simple, and then you just need someone to guide you and say like, hey, only use these few constructs, and you're good to go.
One of my goals for this course is I'll be creating educational like content throughout the course, and I want to create something on namespaces that's like a public thing, because I think the community would benefit from that. Hey, so we got about 10 minutes for 2 o'clock, and I want a couple of things. Number one, Mike, I want to see if you're basically done, or if you wanted to, if there's more
I think
you
that
wanted to talk about this.
No, I think I can't think of anything else that would be, there's endless stuff you could talk about, but the value is diminishing. Yeah.
I wanted to ask, okay, I have 2 quick follow-ups for you on this topic. And then I do want to wrap it up, but is there anything that we need to know, or that you want to tell us about the JavaScript that is emitted by the compiler with respect to externs and Google Clojure Advanced Mode? And before you answer that, like second question, because they're kind of related, I'm curious if you have any opinion on the CLJS oops library, which kind of, I don't know if you're familiar with it, kind of wraps that. Yeah, I just don't know if that's a topic you want to maybe talk about briefly. I know that that's a Google Clojure topic more so than a ClojureScript compiler topic, but I'm curious what your thoughts are.
Yeah. So, so I don't know if you've defined this for the crowd, or what this really means, or if that's what I could perhaps do really quickly. Yeah.
You could also, I'm like kind of asking this question for the video.
Okay.
If that makes sense. But
Okay. So essentially, let's see. So the problem is Google Clojure optimizes your code, it will take the symbols that are in that code and make them tiny. So like you might have a call to count, and that might just turn it into C, for example. Like it takes all these symbols and basically shrinks them down into like 1 or 2 letter abbreviations. And it does that across the board. It's a whole program optimization step to basically make all of your code that much smaller without really changing the meaning of any of it.
Yeah, just to clarify, we're talking about the Google Clojure compiler right now, not the ClojureScript compiler.
Yes. Okay. And the problem is if you're calling out to some external library where you really do need to like basically call that function directly as by its unmodified name, then if you just let Google Clojure Compiler optimize your code and you don't have that other library visible to the compiler, you can run into this problem where your symbols get shrunk down and they no longer map to what they should have been to call this thing. And I think that happens, you're speaking to CLJS oops, where this oftentimes happens too if you're accessing properties on objects by string rather than by like their actual symbolic name. The Clojure compiler will just say, it'll trust you, I think. And it'll just like, I think you can use strings to like work around this at times. I think that's what you're getting at with the oops thing. In my opinion, let's see. So
yeah, I'm curious. So I mean, for the class's benefit, this will be a topic we're going to get into. Like we're going to write a program that breaks in advanced mode, and I'm going to like teach them how to like fix it. But I wanted to know I'm curious if you had an opinion about that.
Yeah. Okay. So, there is, the normal way to deal with this is you declare in an external file saying, these are my externs, please don't mess with them. You know, these are the symbols that you cannot change because if you do, my program will break. And that's one thing, is like this extra linguistic thing that says, hey, don't mess with these things. And then the other opposite extreme is to use something like CLJS oops, or even just like the normal interrupt thing to like change the code of your program so that it's using strings in certain places so that it will not break things. And I kind of found that last thing to me problematic in that it's like, man, I got to change my code to make it work. I would rather like this. Part of me has this purity argument where I don't want to change my code. I want my code to actually work. So I used to previously always kind of, if you asked me, I would favor doing the externs thing just to keep my code pristine and not change, so that it is what it is and I can read it and it's not ugly looking and I don't have strings in there and stuff like that. And these days now there's this infer externs feature that David Nolan added, that basically in a lot of cases can look at your code and infer that you're calling to something external, and it will write that external file for you, the externs file for Google Clojure. And I think if you can get away with that, and I think we are at a point now where you can, and in a lot of cases, successfully use that pattern, then that leaves your code being really clean. And all you really do is at the top of your file, you put this infer externs declaration. I can't remember the exact name for it, but it basically tells it, hey, please, for this file, infer if you see me calling any external things outside of ClojureScript, take those and stash them away in this thing so that you let Google Clojure compiler know not to mess with them. That's so my opinion. I tend to like, just because of purity reasons, I tend to lean towards avoiding trying to muck with your code with the strings. But I think other people fall on the other side of that fence too. And they're like, I know exactly what I'm doing. I'm going to call this thing that I know I don't want, the Google Clojure compiler to mess with. And therefore I'm going to like change my code and tweak it a little bit and use a string here. Or oops. I think oops ultimately like wraps that construct to make it a little bit more palatable. Like it makes it look more straightforward.
Yeah.
So
cool.
So that's my opinion. Is I like this argument of keeping the code clean and not changing it, but I can see people going both ways on that subject.
Very cool. Very cool. Yeah. I think this is kind of a topic outside of the compiler, but I think I fall into the oops camp. But this will be it just for everyone's edification. This will be something that we discuss in like, I don't know, a month from now or something. So,
cool. You need it because your code will break if you don't deal with it at some point.
Yeah. I'm actually like looking forward to the project where the code breaks and we have to go in and fix it and stuff. But okay. So, all right. I mean, I've got 155. This has been 4 amazing hours, right?
Yeah, it's a lot longer than I thought.
No, I love it. I love it. And I mean, I know that my brain is fried. I am sure that Students' brains are fried. I just want to know if anybody has any last questions or comments, or if Mike, if you have any final thoughts, or yeah, the floor is open for anybody. You guys got all that, right? Pop quiz.
I think everyone's
pop
probably
quiz.
dead now. It's kind of like
Pop
that.
quiz on Tuesday. So yeah, I mean, Mike, oh, go ahead. Who is someone?
It's going to be cool to run into this stuff in the future, but yeah, right now it still seems a little bit far off. But.
Yeah, brain is on the floor.
Yeah.
Very cool.
Yeah, it might be the case where like later on, once you've learned more of this language, you can review some of this stuff or recall it, and say like, oh, that's what that,
Yeah.
And if you're a little worried and you're like, ah, man, none of this stuff we talked about today, you need to know. I would argue it's all just stuff that's in the compiler. It's all just mind tricks. The whole compiler could change tomorrow and it'll still work. And everything I just told you could be wrong. So you fortunately don't need to understand any of this stuff. It's all just there to help you. Like you might, to satisfy your curiosity. Like, how does this lawnmower work? Like, yeah, maybe there's a nuclear powered one tomorrow, but this is the way it works today.
Cool. All right, I'm going to turn the video off and then we can kind of just do like a quick class wind down.
Cool.
Before I end, I just want to pitch, if you're watching this video on YouTube and this interests you and you'd like to become a better programmer and learn ClojureScript, please check out cljs.pro or reach out to me, and we'd like to see you in the next class. Otherwise, thank you for watching.